Hey people, and welcome to this video. In this video, we'll be working on the grade 12 Mathematics Paper 2 for June 2024. And this is specifically from the Gauteng province. Just remember that this paper is worth 150 marks and the time allocated is 3 hours. Okay, moving on to the instructions. Remember to round off to 2 decimal places unless stated otherwise. The diagrams are not necessarily drawn to scale, and you do have an information sheet with formulas at the end of the question paper. Okay, with that being said, let's get into this video. Question 1.1 says, the data below shows the marks out of 100 obtained by 16 learners in a mathematics test, test 1. And the first question, 1.1.1, says we have to calculate the mean mark of the test. Okay, we can use our calculator to do this. So go to mode and then stat. Now this is just a data set with one variable. So you're going to go to 1 VAR and then put in your data points. And then once recorded, press AC, Shift and 1 and go for variable, okay, VAR, and then just go for the option that shows you the mean. So it will look like that. So the mean of our values is 61 point, and I mean they're marks out of 100 though. So we can just round off to 2 decimal places. That's fine. So that's going to round up to 38. So 61.38, and that is the mean. Moving on to the next question. Question 1.1.2 asks us for the standard deviation. So the standard deviation, just again press Shift and 1, go to variable, and then you'll find your standard deviation. That is the standard deviation. So the standard deviation is 19 point, and then that just rounds down to 6.3. Okay, moving on to the next question. Question 1.1.3 says the number of learners. So we need to calculate the number of learners whose marks are outside one standard deviation of the mean. Okay, so outside. So you're looking at the mean. So we'd have to find out what within a standard deviation of mean looks like first. So this would be a standard deviation greater than the mean. So we'd add a standard deviation here and a standard deviation below the mean. Okay, so minus a standard deviation. So it looks like this. It's the mean minus a standard deviation, and the mean plus a standard deviation. Okay, and we're just trying to find out how many learners lie outside this. Okay, so learners outside this. So if you had to put these down as point values, right, then we're looking for the number of learners who had marks lower than this, okay, and marks higher than this. Okay, within one standard deviation of the mean would be values greater than this number, but less than this number. So that would be within, but we're looking for outside one standard deviation of the mean. Okay, so let's find these values. So we're going to say the mean plus the standard deviation, that's 61.38 plus 19.63. Okay, I mean minus, and then here we add, so 61.38 plus 19.63, and let's get those values. So that is 41.75, and then we can just change that to a plus, and so that is 81.01. Okay, so this is what we have. We need to find the values that are less than this but greater than this. Okay, numbers less than 41.75. So numbers less than that, we've got, so numbers less than that, 26, 38, 32. Okay, so that's it for the numbers less than 41.75, and then the numbers greater than this. So numbers greater than 81 point, well, we have 92, we've got 83, 94, and yeah, that's it. Okay, so that's 2, 4, 6. Okay, 6 learners. Okay, so that's 5 and 6. So it's 6 learners. So we can finally just conclude. You don't have to write the whole sentence. You can just tell them these would be 6 learners, and that is our answer. Okay, moving on to the next question. Question 1.2 says, the 16 learners referred to in question 1.1 above wrote a second test, and the box and whisker diagram shows the distribution of marks obtained by the 16 learners in the two tests. Okay, and they want us to describe the skewness of the marks for test 1. Okay, so the skewness of the marks, let's look at that. You see, for you to determine the skewness of the marks, don't focus on the way this looks and say, it looks like it's more to this side. Don't do that. Focus on the median, okay, Q2, and how close it is to Q1 versus Q3. If it is closer to Q3, then it's skewed that way. We'll talk about the skewness. And if it's closer to Q1, it's skewed that way. So it can look visually deceiving. So you can actually just find that difference. So on our calculator, we can quickly just find out how far apart it is. Q2 is at, we can see that this is 62, right? So we can just say 62 minus, and just to see how far apart it is, minus 46. Okay, that's 16. So 16 units away like that. And then here we can say this is, okay, it looks like it's counted in intervals of 2 because 70 is 72, 74, 76, 78. Okay, so this is 76. So let's say 76 minus, and then that value of Q2. That's 62. That's 14 units away. So remember, if it's closer to a specific quartile, then that is how it's skewed. So between 16 and 14, you can see that the distance between these two is shorter. So it's skewed this way. And now how you find out how it's skewed, you can think about it like this. If you were standing but facing the front, okay? So you're facing the front, and if you were facing the front, then this over here would be your right-hand side, and this would be your left-hand side. So this is skewed to the left. So we can say it's skewed to the left or negatively skewed. Okay, that's our answer. Moving on to the next question. Question 1.2.2 says, which test was easier for the learners? Give a reason for your answer. Okay, so looking at this, where do you see the performance is better? The performance is better in test 2 because you can focus on the median, okay? 50% of our data set, the learners. So 50% of the learners here, you can see that 50% of them got higher than 66. And then, the other 50% got lower than that. But here in test 1, 50% of the learners got a mark that was higher than 62. Okay, that's where 50% of your data set is. And 50% is over here as well. But speaking about performance-wise, half the class got higher than 66 here, and then half the class got higher than 62. So clearly, test 2 was easier, okay, because there's a better performance there. So we can tell them this is test 2, and our reason, 50% of the learners in test 2 scored marks that were above 66 out of 100. Okay, so 50% of the learners scored above 66 out of 100 in test 2, while 50% of the learners scored above 62 out of 100. So we can see that that is a better performance. Okay, moving on to the next question. Question 1.2.3, the last question for question 1 says, how many learners scored more than 84% in the second test? Okay, so in test 2, we go to 84%, which is over here. So how many learners are in this category? So learners who scored more than this would be here. Remember how your box and whisker diagram is divided. Okay, this represents 25% of your data set. This is 50%. This is 75%. So if all of this is 75%, you see that this little part is 25%. So we just need to know how many learners there are in total, and we'll be able to know how much 25% of the learners would be. So remember that they said by the 16 learners. So there are a total of 16 learners. So we can just say 16 multiplied by 25%. So 25 over 100. And this is just 1 over 4. So a quarter of 16, which is 16 divided by 4, and that is 4. So there are exactly 4 learners that scored more than 84%. And that is it for question 1. Question 2 says, in a survey, a group of people were asked about the total distance they had traveled from their homes in the last week of December 2023. The data collected is represented in the frequency table and ogive, the cumulative frequency, below. Okay, so we've got our frequency with A and B missing and the cumulative frequency. Okay, so we can definitely find that because we have both. Okay. The first question is, how many people participated in this survey? So we can see that we can't add these up, unfortunately, because we don't know what A and B are. But we can actually see that from here. You see that this is the cumulative frequency. So this is a result of adding your frequency values. When you keep adding them, at the end, you will end up with a total number of people in this study. So the highest point will tell you the total frequency. So we can see there were 400 people in this survey. So we can say 400 people. And that is our answer. Moving on to the next question. Question 2.1.2 says, determine the values of A and B in the table above. Okay, and this is where we're going to use both together. You see, the graph shows you the cumulative frequency per data point, right? And this part is just showing you the single frequency. So here's the relationship and how it works. We can take advantage of this and find the cumulative frequency. So cumulative frequency. And this is how it's going to work. So first we have 20. So that just goes 20, that's all. So you see why this is on 50. It's because 50, this x value of 50 will always go with a y value of 0. Okay, so that's always going to be your x-intercept. So that's why that is 50 and 0. Then the next x value that we have, that's what goes with this cumulative frequency value of 20. So this is 20. And then the next one, you see that that one is at 50. So the reason why is because we said 20 plus 30 gives us 50. And that's why 150 and 50 go together. So that is 50. And here's how we find A. So we're going to say 50 plus whatever this is to get our value here. So we'll go to 200. And at 200, you see that we are right at 100. So that means 50 plus A gives us 100. That is the cumulative frequency value we have there at 200. So what does that mean about A? A is equal to 50 plus what gives you 100? 50 plus 50. So A is equal to 50. We got A, and let's just get to B. So the next point we have is at 250, and the cumulative frequency value is 200. So this is 200. So 100 plus what gives you 200? That is 100. And there we go. So B is equal to 100. A equals 50, B equals 100, and that is our answer. Moving on to the next question. Question 2.1.3 says, use the ogive or table to estimate the number of people who traveled between 100 to 300 kilometers. Yeah, I see why they say use the ogive or the table. You can use either one. Okay, you can even use it together. So from 100 to 300 kilometers, how many people were within this? How many people traveled within this distance? Well, you can go to 100 and we can see that the cumulative frequency value there is 20. And then go to 300 and then find out what that cumulative frequency value is. We actually can find it because, okay, the next one is 300. So this is 300 and the cumulative frequency value would be 200 plus 80, which is 280. So we know this is 280, meaning the total people who travel from 100 kilometers to 300 kilometers would be the 280 people minus the 20 people. It would be the people within here, because those are the ones that map from that 100 kilometers to that ogive, that's 20, and then from 300 to the ogive, that is 280. So we'll just say 280 minus 20, and then we'll find out how many those people are. If you say 280 minus 20, this is 260 people. So we can just tell them it's 260 people. And that is our answer. Moving on to the next question. Question 2.1.4 says, if all the people who traveled more than 350 kilometers were removed from the survey, how will this affect the median of the data? Okay, let's look at this. So if all the people who traveled for more than 350 kilometers, meaning there would be a cut off here. We would cut this part off. No more data here. And our data would just go like that. So how will this affect the median? Well, think about what the previous median would have been. And they're saying how will, so it's not really a calculation question. We don't have to calculate things. The previous median, because the highest cumulative frequency, there's a total of 400 people. That median will be found at half of 400, which is at 200. So that median, okay, the median travel time would have been here at 250. But now this doesn't exist anymore. They cut off. So the new median would be half of this new maximum, which is 350. So that new median would be around, we'll go to a cumulative frequency of 175. Okay, do you see how that decreased? It used to be up here at 200, and then it went below here. So the median would just decrease. That's all that would happen. You're cutting off this chunk of people. So it just becomes a lesser value. Okay, so that is what will happen to the median. It will decrease. Moving on to the next question. And the last question, 2.2. If the estimated mean of the data below is 16.4, estimated mean is equal to this, then what is the value of t? I feel like this is that question they threw in because they were like, we were very generous here. Let's just make you work a little. Okay, so let's see. We just have to calculate the estimated mean. So with the estimated mean with group data, because you don't actually have actual values, the frequency is just telling you how many people were in this category. We're not going to go to each people. I'm not really sure what this is talking about. Is this actually, it's not the same data. Okay, I don't think it's not the same data. It's just a new data set. Okay, so let's just say these were people, right? And I don't know what these numbers are, but they're not telling us how many people are in this category. So because of that, it becomes an estimated mean. It's not like we went to each person and said, okay, how much did, I'm not really sure what these numbers are. So, okay, let's just give a scenario. Let's say these were the number of items that people buy online. Okay, there were 13 people who bought 0 to 10 items in a month. And then people who bought 10 to 20 and so on. So it's not like we're going to each of the 13 people and asking them, hey, how many items did you buy? And how many items did you buy? So we didn't do that. They just grouped them into one category. People who bought from 0 to 10. Okay, for example. So because of that, it becomes an estimated mean because we don't actually know each data point. We don't know how many items are here. So because we don't know these, we're going to find a midpoint of them. It's really just like using the average of these. So the midpoint of each of the class intervals. So from 0 to 10, the middle would be exactly 5. You can just say 0 plus 10 divided by 2. From 10 to 20, the midpoint is exactly 15. And then here it's exactly 25. And then here's exactly 35. Again, I'm looking at it as if these are items that people buy online, right? You can't just say, okay, there were 5 items bought and then 15 items bought. No, there were 13 people in this category. So it's not just 5 items bought in total. It's 5 times 13 because the 13 people who bought were saying that they bought 5 items each. So you need to say the midpoint multiplied by the frequency. Okay, so let's multiply those. 5 times 13, that's like 130 divided by 2, which is 65. And then here, because this is t, we're still going to say t times 15. So this is 15t. We'll keep that in mind. And then 12 times 25. Okay, let's just see. 12 times 25, that is 300. So here we have 300. Let me not put it in red. 300. Okay, 4 times 35, 140. Okay, 140. And now this represents the total items, really. Okay, now to find the estimated mean, which they already found, the estimated mean is found by taking the sum of all your values. Okay, all your values, but we'll just take that as, yeah, you can call it X, it's fine. And then you're going to divide by the total amount of people that they are, because it's just the mean, okay, the average. So divided by the total amount of people, which we can just call n. Okay, so this is equal to, the estimated mean itself is already 16.4. 16.4 is equal to the sum of all these values. So let's add everything up, but we'll just still have 15t, so plus everything else. Okay, so everything else apart from the 15t give 505. So we're just going to say plus 505. Why am I writing 5 like that? 505 divided by, and then the total frequency. So just add everything up. These two already give 25. Then that's 29 plus t. Okay, so we have t plus 29. Great. And now we can find t. So this is just an equation. You have a fraction here. You can make this a fraction. 16.4, we can just make it a fraction straight away. 16.4 is 82 over 5. So I'll just say 82 over 5 is equal to still all of this. Okay, so now we can just say 15t plus 505 over t plus 29. Okay, cross multiply. So it's the 82 times the t plus 29. So 82 times t is 82t. And then what's 82 times 29? That is positive 2,378. Okay, and then 5 times 15, that is the t and the t, the 75. Okay, so 75t, I don't even know why I'm calculating like that, but there's a calculator in front of me. 5 times 505, and then that's positive 2,525. Okay, and now we can just solve for t. So transpose, that is 82t minus 75t is equal to 2,525 minus 2,378. And then that is a 5 and a 2, which is 7t is equal to, and let me just subtract that. So 2,525 minus 2,378, and that is 147. Okay, and then if you divide both hand sides by 7, t is finally equal to, so divided by 7 is 21. And that is our answer. Okay, so that is the value of t, and that is it for question 2. Question 3 says, in the diagram below, the equation of AD is 2y plus x is equal to 11. So that's the equation of this line. And then they also tell us that M is the midpoint of the straight line joining B and C. So this is the midpoint. The angles of inclination of AD and BC are alpha and beta respectively. E and F are y-intercepts of AD and BC respectively. Okay, and the first question 3.1 says we need to determine the coordinates of B. Okay, so find the values of A and B. Well, we have a straight line here, and we are told that this is the midpoint. And we have this endpoint over here. So we can go ahead and use this to find this endpoint. So we have the midpoint, meaning we're going to use the midpoint formula. So the midpoint formula looks like this. Okay, and then we are going to substitute. So we're looking at this as if we're finding the midpoint of BC, but we already have it though. So with that, we're just saying x1 is a, that's a, plus x2 is 3. Okay, so that's a plus 3 over 2. And then b plus this y value, which is 4 over 2. Okay, now we already have this midpoint. It's 1 and negative 1. So we say that we already have that midpoint, 1 and negative 1. And so they are equal. And we can equate now their x values and their y values since they represent the same thing. Okay, so it means that their x values are equal and their y values are equal since they represent the same thing. So it means a plus 3 over 2 is equal to 1, and then b plus 4 over 2 is equal to negative 1. Okay, if we multiply both hand sides by 2, we get a plus 3 equals 2, and then transpose 3, a is equal to 2 minus 3, which is negative 1. And then here, we'll multiply both hand sides by 2, so b plus 4 equals negative 2, and then transpose 4, so b equals negative 6. And there we go, that is b. So it means that b is simply the point negative 1 and negative 6. And that is our answer. Moving on to the next question. The next question asks for the gradient of BC. Okay, so we know what b is now. It's negative 1 and negative 6. So negative 1 and negative 6. And we can find the gradient of BC. So let's just take these points, B and C. Okay, so to find the gradient of a line, we use this formula. And I'm just going to go in the order of top minus bottom. So that's negative 6 minus 4 over negative 1 minus 3. And so that gives us negative 10, that's negative 4. So they become positive, but they have a common factor of 2. So that is 5 over 2. And that is the gradient of line BC. Moving on to the next question. The next question says, determine the size of theta correct to 1 decimal place. Okay, so the size of theta's over here. Okay, so it's not beta that we're just trying to find, but you can see the relationship between these. You see, we have the gradient of BC. They just asked us to find it. So the gradient of BC is useful to find beta, but then how does this relate to theta? Well, do you see that we have a triangle here? And alpha, the angle of inclination of line AD, is the exterior angle of this triangle. So it's equal to the sum of the two opposite interior angles. So we can just find this exterior angle and then find beta, and then we'll be able to find alpha. Okay, let's go ahead and find beta because we have its gradient. So the gradient is 5 over 2. We'll say tan of beta is equal to the gradient 5 over 2, and beta equals arctan 5 over 2. So let's see what that gives us, and we can leave it as 68.1985. Okay, I'll leave it like that for now, and I'll just work with those 4 decimals. Okay, and then let's find the size of alpha. So alpha will be found by using the gradient, but we have the equation of this line, so we can find the gradient of alpha. So 2y plus x equals 11, and let's find the gradient. 2y plus x equals 11. If you put it in the standard form of the equation of a straight line, y equals mx plus c, then we will see the gradient. Okay, so make y the subject. 2y equals negative x plus 11, and then divide both hand sides of the equation by 2. Therefore, y equals, is an invisible 1 here. So this is negative 1 over 2x plus 11 over 2. Okay, and that's the equation of line AD that we have. So since this is AD's equation, we know that the gradient of AD is equal to negative 1 over 2. So we can also find that angle of inclination. So it's specifically the angle of inclination of AD, which is alpha. So we can say tan of alpha equals negative 1 over 2. And then to find this angle, we're going to say arctan of negative 1 over 2. But this is going to give us the negative. So we don't want that negative. As we can see, that angle was an obtuse angle. It's not this one that we're referring to. Okay, so it's an obtuse angle, not this part. So to ensure that we get that, we're going to say plus 180 degrees. So plus 180 degrees, and there we go. We can see now that obtuse angle. Okay, so we can just put that down. It means that alpha is therefore equal to 153.4349 degrees. And now we can finally use this to solve for theta. So theta is equal to, if we say that alpha is equal to the exterior angle is equal to beta plus theta, then to find theta, you simply say alpha minus beta. Okay, so theta equals alpha minus beta. We don't really need reasons for this. Okay, theta is equal to alpha minus beta. And then let's put down our values. So this is 153.4349 degrees minus beta, which is 68.1985. Okay, and then just make sure that you round off to one decimal place like they said. So this is 85 point, and that's just going to round down to 2. Okay, 85.2 degrees, and that is our answer. Moving on to the next question. Question 3.4 says we need to determine the equation of line BC. Okay, so BC is this line, which we have the gradient of, and we have 1 point on this line. We have 2 points, but we can use C because, both values are positive. So that's 3 and 4. Okay, so the gradient of BC, remember, is 5 over 2, and then we're just using C. Okay, so I'm going to use this equation. Y minus y1 equals the gradient times x minus x1. And so y minus, and we're saying the y1 is 4 and the x1 is 3. So this is y minus 4 equals the gradient of 5 over 2 multiplied by x minus 3. And then just simplify. So we're going to distribute here, and we have 5 over 2x. And then that gives us negative 15 over 2. And when we transpose negative 4, it becomes positive 4. So y is equal to this. And let's just add there. So y equals 5 over 2x. You can just put this over 2 by rewriting it as 8 over 2. So that is still 4. 8 minus 15 is negative 7. So that's minus 7 over 2. And that is our answer. Okay. That's the equation of line BC. Moving on to the next question. Question 3.5 says, determine the area of triangle CEF. Okay, so that is this triangle over here, CEF. Okay, so how do we find the area of this triangle? Okay, so this is what the triangle looks like. And how do we find the area of this triangle? So I would always advise that you try half base times height first, and then, go to alternate means of finding the area. So in this case, can we actually use a half base times height? Well, we can't really draw the height like this, okay? But we can actually draw the height like this. So look at EF as the base of this triangle, and then the height will be drawn like this. So from C, we'll go to, not like that, but from C, it's going to be a horizontal line, okay? And that will be the height. So you see this horizontal line, this line will be perpendicular to the y-axis because it's a line that is parallel to the x-axis. It's a horizontal line. And we can find the height. We can find this height. So it's going from the x value of 0, and then it goes till this point C, where the x value is 3. So it means it just goes 3 units to the right. This height is 3, and we can just take the base as EF. Okay, so we have the equation of AD, and we also have the equation of BC, so we can find their y-intercepts. Okay, let's find the y-intercept of AD. Okay, so let's find the y-intercept of AD and CB. Okay, so this is line BC, right? We're going to take the y-intercept. We can see it there. So the y-intercept is negative 7 over 2. That means we know what F is. This is negative 7 over 2. Great. And we just have to find AD's one. Okay, So taking the equation of AD, which we put this in standard form at some point. Okay, we already had AD in standard form. So, okay, here, AD. It's good to label your lines. So it means that its y-intercept is 11 over 2. Okay, we're just going to have to write these down. So we know that F was 0 and negative 7 over 2. And we know that E that's 11 over 2. So this is 11 over 2. So it's 0 and 11 over 2. Okay, so that would mean that EF, the base of this triangle, we'll find by saying 11 over 2 minus negative 7 over 2. Okay, so this is equal to, if we say 11 plus 7, that is 18. 18 divided by 2 is 9 units. Okay, so EF is 9 units. And then remember the perpendicular height that we found, that was 3 units. So that means that the area of triangle CEF is finally equal to, we'll say, half multiplied by EF, which is the base, half base times height, multiplied by the perpendicular height. So just say perpendicular height. Okay, and then this is going to be equal to a half multiplied by 9 multiplied by 3. Okay, 3 times 9 is 27. Half of 27 is 13.5. So that is 13.5 units squared. And that is our answer. And that is it for question 3. Question 4 says, the diagram below shows a circle with center P and the equation, so this is the equation of the circle. The circle cuts the y-axis at points R and S, okay? And then we have RT is a tangent to the circle at R and cuts the x-axis at T. Okay, so notice that theta is this angle formed by the y-axis and this line. So 4.1 says, determine the coordinates of P as well as the radius of the circle. Okay, we have the equation of the circle. So given this, we need to ensure that it's put in the standard form of the equation of a circle so we can clearly see the center and the radius, okay, the length of the radius. So let's rewrite this x squared plus y squared. Let's just rewrite this first. And we need to ensure that everything with x is next to each other, because in order to put this back in the standard form of the equation of a circle, we need to complete the square on this. So we'll rewrite this as x squared minus 6x plus y squared minus 4y is equal to 12. And now to complete the square. So you're going to take these two terms, and you're going to complete the square on them separately. So this will be x squared minus 6x, and then you take the coefficient of x and you divide that by 2. So that will be negative 3. And you're going to add negative 3 all squared. And then we're going to do the same thing for this part. So plus y squared minus 4y, and then we're going to take the coefficient of y, which is negative 4, and divide it by 2, which is negative 2. So we're adding negative 2, and we square that. Now, this is an equation. So what you do on the one side, you must do on the other side. You see that we have added by this number squared and this number squared. We need to do the same thing on this side. So on the right-hand side, we say plus negative 3 all squared and plus negative 2 all squared. Okay, and now we're just simplifying. You see, if you expanded these, right, they'll become a trinomial and they would factorize like this. So you're going to open a bracket, and inside the bracket, whatever was squared, you're going to put that in here. So that is the x and the minus 3. And then that is all squared, because it was going to factorize to x minus 3 times x minus 3, okay? If you, of course, squared that and you got that number. X squared minus 6x plus 9 factorizes to this. Okay, so that's the first part, and we do the same thing here. So we say plus, and we have y, and that is minus 2, and then all squared, and then this is equal to, and then we just add this. Okay, so that's going to be 9, and that's going to be 4, so they already make on their own 13, and we're saying plus 12, so that is 25. So is equal to 25. Now it is in the standard form of the equation of a circle, and we can tell them the value of P, the center of the circle, and the radius. So P would be, it's in the form of x minus a all squared, a being the x value of your center. So this is 3, and then that's y minus b, so that is 2. That's the center, and the radius is, this is r squared. Okay, it's in the form of x minus a all squared plus y minus b all squared equals r squared. So that's the radius squared, meaning the radius is, the square root of this is 5. And there we go. So that is our answer. Moving on to the next question. Question 4.2 says, show that the coordinates of r is 0 and 6. Okay, so r is on the y-axis. Okay, it's on the circle, but it intersects the y-axis. So it's a y-intercept, meaning to find it, we can simply just make x equal to 0. Okay, and it will be, well, they already told you to find it in this format, so clearly this is going to be helpful. So we'll take this and we're going to make y equal to 0. Of course, we'll have two y-intercepts, but we will choose which one is r. Okay, so we'll make x equal to 0 to find the y-intercept, and this is minus 3 all squared plus y minus 2 all squared equals 25. And so negative 3 squared is 9, and if you transpose that, 25 minus 9 is 16. Okay, so we can just say this is y minus 2 all squared equals 16, and then to solve for y, we square root both hand sides. But this is an equation, so you need to consider the positive and the negative solution. Therefore, y minus 2 is equal to positive or negative 4. And then transpose the negative 2, y is equal to positive 2 plus minus 4. And so y is either equal to 2 plus 4, which is 6, or y is equal to 2 minus 4, which is negative 2. Okay, so 6 or negative 2. Which one would it be? Clearly, this is the negative 2, and this is the 6, okay, because it's the higher one. Okay, so we're just going to conclude that r is the coordinates 0 and 6, and that is our answer. Okay, moving on to the next question. Question 4.3 says, determine the equation of the tangent RT in the form of y equals mx plus c. So RT. We only have 1 point on this. We have 0 and 6. And how do we find RT? Okay, it's a tangent. Okay, it is a tangent, so we can just use the radius. So connect from P to R, and there we go. We have a radius. And remember, we already have the coordinates of P. P has the coordinates 3 and 2. So we'll just say this is 3 and 2. And then remember that the radius and the tangent are perpendicular at their point of contact. So we can find the gradient of the radius and then use that, using the properties of perpendicular lines, to find the gradient of the tangent. Okay, so let's get P and R down. Okay, so the gradient is, well, we don't really have to write the gradient formula. You can just go ahead and find the gradient of PR. So this is equal to y2 minus y1. I'll just start from the bottom here. So 6 minus 2 and 0 minus 3. 6 minus 2 is 4, and that is negative 3. So this is negative 4 over 3. And so if this is the gradient of the radius, then the gradient of the tangent, and it is RT, that is the tangent, would simply be found by saying, because they are perpendicular lines, you simply just switch the numerator and denominator. So that is 3 over 4 and still negative. Then you multiply this by negative 1. Okay, so it becomes positive 3 over 4. That way, if you multiply the gradients of these perpendicular lines, they give you negative 1. Okay, so we have the gradient of RT, and we also have a point on RT. We have R, 0 and 6. So let's find its equation, and R is already a y-intercept, okay? So you can just find it in the form of y equals mx plus c. So y is equal to 3 over 4x, and this is a y-intercept. So c is 6 plus 6. And that is our answer. Okay, moving on to the next question. Question 4.4 says, determine the size of theta correct to 1 decimal place. Okay, so let's look at theta. Theta is on this line, okay, TR. It's really formed by it. But here's something we can do with this. So this is 0 and 6. We have theta over here, and we can actually just draw an imaginary x-axis. So this is just a line parallel to the x-axis, so you can better understand how this angle was created. So you put it right at that point there. Okay, so change the color of it. Now you can see that, actually let me just remove this for now. You see with this angle that we're looking for, it's created with a 90-degree angle and another angle. So if you go from the y-axis to this line parallel to the x-axis, that's 90 degrees. Then we'd have to figure out what exactly this angle is. This angle, okay, if you go from this line parallel to the x-axis to the line TR, that extension, you see that it's the angle of inclination of TR. And to find the angle of inclination of TR, okay, do you see that they are vertically opposite? Okay, the straight line, the horizontal line, and TR cross. And so this angle, whatever this is, that is that angle. So this is the angle of inclination of TR. And we already have the gradient of TR. So we can actually find this, and then you just add 90 degrees to it. And that would give you the entire theta. This angle plus 90 degrees, because these are vertically opposite. Okay, so let's find that angle of inclination of TR first. We know that the gradient of this line of RT/TR is 3 over 4. So we'll say tan theta of RT equals 3 over 4. And so that means theta of RT is equal to arctan 3 over 4. And let's go ahead and find this angle. Okay, and then we'll just add, yeah, I think at this point you can just, because it's going to round off. So I'll leave it like this and then just say that theta is equal to 90 degrees plus theta of RT. Okay, so theta is equal to, okay, just to avoid confusion, I'm going to still say 36.869. Okay, not rounding off yet, but then just add a 90 degrees to it. That's all. So take that and then add 90 degrees. And there we go. So theta is finally equal to 126 point. Remember they said round off to 1 decimal place. So that is 126.9 degrees. And that is our answer. Question 4.5 says, a vertical line is drawn as a tangent to circle P at Q, which is A and B, where A is greater than 0. And we need to write down the coordinates of Q. Okay, vertical line, it's drawn to the circle at Q, okay, where A is greater than 0. It's vertical, so it's a standing line. Okay, so a vertical line. So for it to be drawn as a tangent, it can't be this side because they said that A is greater than 0. Okay, so that X value of the point Q is greater than 0. So the only other place it could be a tangent to this circle would be here. Okay, where A is greater than 0, the X value is positive. So what they're saying is we have this point Q and we have A and B, and so A is a positive value. So what is this point Q? Okay, so it touches the circumference of the circle. That's what we know. So that simply just means that, you see, if it touches the circumference of the circle and it's a vertical line, right, it will be perpendicular to the radius, which is a horizontal line, okay, because this is a vertical line and the radius and the tangent are always perpendicular at their point of contact. So it's perpendicular to this horizontal radius, meaning if this is 3 and 2, okay, the X value is 3, it means that we know that the radius of this circle, we already found the radius, that was 5 units, right? R is equal to 5. So it means that we went from 3 and we went 5 units to the right to get to Q. And so the X value, A, is 8, okay, because 3 plus 5 is 8. And the Y value, it stays the same really, because this is 3 and 2. This is a horizontal line, so they share the same Y value. So this is 2, meaning There we go. That is 2. Okay, P has the y value of 2, and so does this because it is horizontally in line with Q. Okay, so this is 2, and so the coordinates of Q are 8 and 2. And that's our answer. Okay, we can just tell them Q is 8, and there's not really any calculation. The only calculation is that A, saying that we get that by saying 3 plus 5, which is 8. Therefore, Q is 8 and 2, and that is our answer. Moving on to the next question. Question 4.6 says, for which values of K will y equals positive 3 over 4x plus K be a secant to the circle? Okay, we already had this equation. This was the equation of the tangent. So not really the equation of the tangent, but yes, it's the gradient of the tangent. So they want to find out for which values of K will this line be a secant to the circle. Okay, so when that equation y equals 3 over 4x, okay, 3 over 4x is a tangent, this is where the K value is equal to, so that's the equation of the tangent, okay? So where the K value is equal to 6. So when we have the K value equal to 6, it's a tangent, but we need to find the values of K for which it will be a secant. Okay, let me just remove these because they don't really seem necessary. I'll leave the points, but we don't really need these. Okay, so to find out for which values of K it will be a secant, let's redraw this line and just see. So you see, if you take this line and it has that same gradient, we just need to see where it will be a secant. The minute you move it below this point over here, okay, so where K is equal to 6, the minute you move it below 6, where that y-intercept is lower than 6, it becomes a secant. It's intersecting the circle, cutting through the circle at 2 points. So there, it's a secant, keep being a secant until it gets to this point over here. So we need to find out where does that happen. And we need to ultimately find out what exactly the y-intercept will be at this point, because we're trying to find out the values of K. Okay, and K is that y-intercept. So we need it to get to this point, and let's see how we can find this. Okay, we can do this in the same way we found the equation of the tangent. Why don't we just extend this radius? Extend it to this point so it becomes a diameter. And then we can find out where it intersects with this tangent, because this is the tangent we'll focus on. And we can find out this point simply by using midpoints. We know what R is. R is 6, 0, and 6, right? And this is the other endpoint of the diameter. So we can just use this and find this endpoint. So I want to find out what exactly this point is. And so I'm going to use midpoints. Okay, so the midpoint formula, we're just going to go ahead and we already have the midpoint. So we're just saying we have this is x1, this is x2. I'll just take this as x1 instead, and that's x2, and that's y1, and that's y2. So, okay, we've labeled them, and now we can just say x plus 0 over 2, and then y plus 6 over 2. And this midpoint is equal to this midpoint that we already have, that center of the circle, which is 3 and 2. So we're just saying that's just going to be x. X over 2 equals 3, and y plus 6 over 2 equals 2. Multiply both hand sides by 2. X is equal to 6. Here, multiply by 2. Y plus 6 equals 4. Y equals 4 minus 6, which is negative 2. So this point is 6 and negative 2. Great, we have this point. Okay, so 6 and negative 2, we have this point now. We know what this is. So why is this important? Because it will find the equation of this line, the tangent with this same gradient, but that is a tangent to the circle at this point. And this is the last place it will be a tangent to the circle. If you move it anything further than this, it no longer intersects, okay? And if you move it above this, it will be a secant. So we need to ensure that whatever that y-intercept is, okay, whatever that value is, K just needs to be anything above that, but anything below 6, and then that will make this a secant and not a tangent. Okay, so now the goal is to find the equation of this. We already have the gradient of the tangent, so we don't even need to use this gradient. So the gradient of the tangent is already 3 over 4, and we have to find out what the equation of this line is so we can find that y-intercept. Okay, so the gradient is 3 over 4, and we're saying y minus y1 equals m times x minus x1. And so the x1 and y1, this is the point on that tangent. So this is y minus negative 2, which becomes a plus 2, is equal to 3 over 4 times x minus 6, equal to, we'll say 3 over 4x. And then if we multiply here, 3 over 4 times negative 6, they have 2 in common, so divided by 2 is 2. Divided by 2 is 3. So this is negative 9 over 2. Okay, negative 9 over 2, and then transpose the 2, minus 2. So y is equal to, the equation of that tangent is 3 over 4x. And we can just say negative 9 over 2 minus 4 over 2. So that's going to give us negative 13 over 2. Okay, so negative 13 over 2. And that is that y-intercept. So here's what we're saying about k. This will intersect again here at negative 13 over 2, right? And for this to be a secant, then k, that y-intercept of the tangent, should just be anything that is above negative 13 over 2, but nothing beyond this y value of 6, because if it goes beyond, it no longer intersects, and we can't even call that a secant. Okay, so that's what it needs to be. K must simply be greater than, so we'll say k needs to be greater than negative 13 over 2, but less than 6. And that is our answer. Okay, so that is it for this question. Moving on to the next question. Question 4.7 says, another circle M with equation x plus 3 all squared plus y plus 2 all squared equals 36. Okay, it looks a lot like the circle that we have, but the radius is 36. Okay, so this circle is drawn, and the question is, will circle M touch or cut P, or will it neither touch nor cut circle P? Okay, show all calculations to determine your answer. Let's just speak about how circles, intersect or don't intersect, or intersect at 2 points. So if you have 2 circles and they intersect, let's just say they intersect at 1 point only. What's going to happen is you'll notice that if you calculate the radius of the one circle and you add it to the radius of the other circle, so the distance between them would be exactly the same as the sum of their radii. Okay, so that means it intersects at 1 point only. Now, if these circles were to intersect at 2 points, okay, so we want to see an intersection here and here, then look at the relationship between this distance between their centers and the radii. So that distance, right, if you connect that, do you see that that would be shorter than the distance between, or the sum of their radii? Because you're going to add from there to that circumference, from here to this circumference, and so that is going to really just be shorter. So the distance will be less than radius 1 plus radius 2. And then if the circles do not intersect at all, then you will see that the distance, as you can see, that's much larger now. The distance between their centers would be greater than the addition of their radii. Okay, so the distance will be greater than radius 1 plus radius 2. That's all we need to focus on. Okay, so let's go ahead and find this. Okay, so let's look at each circle. So we have the circle with center P, and its points are, okay, we had 3 and 2, and we knew that the radius was 5. And then the circle with center M that we have here, the center is negative 3 and negative 2, and we can see that r squared is 36, meaning the radius itself is 6. So let's find the distance between their centers, and then we'll add the radii. Okay, so using the distance formula, we just say the square root of x2 minus x1. So I'm just going to say negative 3 minus 2 all squared plus negative 2 minus 2 all squared. Okay, let's see what we get. And we get the square root of 41. And then you can also just put this in decimal form. So it's 6.403. Okay. And we're going to compare this with adding the radii. So take the radius of the circle P and add this to the radius of the circle, the center M. We get 5 plus 6, which is equal to 11. Okay, so you can see that the distance is less than the addition of the radiuses. So P plus R with M. Okay, we can see that 6.403 is a value less than, we can just say PM here so they know. Okay, it's a value less than 11. So what does that mean? Okay, if your distance is less than the addition of the radii, it means they intersect at 2 points. Okay, so they intersect at 2 points. So you can actually just conclude that, yes, they will intersect at 2 points. Okay, so in conclusion, circle M will touch circle P at 2 points or twice. Okay, and that is our answer. And that is it for question 4. Question 5.1 says, simplify the following expression without using a calculator. Okay, so we have tan negative x. Now our angle is negative, and when your angle is negative, you can simply just add 360 degrees to this. So this is tan 360 degrees minus x, and seeing that it's 360 minus x, that is in cos's quadrant. So we know that in this quadrant, tan is negative. So this simplifies to negative tan x. And then we'll multiply them by sine 90 degrees plus x. We can simplify that using cofunctions. So it becomes positive cos x. And then plus we have sine 2x. So this is a double angle identity. So it expands to 2 sine x cos x all over, and this is 360 degrees plus x. Okay, so you already have 360 degrees and you're adding an angle. So this is going to be an angle greater than 360 degrees. When your angle is greater than 360, you simply subtract 360 degrees from it. Okay, so if it's negative, add 360. If it's over 360, subtract 360. So this now becomes positive 2 cos, and you see 360 is gone. It's cos x. Okay. We have tan. We can go ahead and expand this to sine x over cos x. So this is negative sine x over cos x using its identity. And it's multiplied by cos x. Plus, now here in this term, you see how 2 and 2 cancel. Cos x and cos x cancel. And we're left with sine x. Okay. Initially, and even here, we had 2 terms. So this is one term. And then it's separated by the plus sign. Terms are always separated by plus or minus signs. And then another term. So it's still 2 terms. This is one term and this is one term. And we simplify expressions term by term. So here you see that cos x and cos x will cancel because they are common diagonally. Okay, so they're under one fraction. And so they cancel because they're common. And this is now negative sine x plus sine x, which simplify to 0. And that is our answer. Moving on to the next question. Question 5.2 says, given that sine 27 degrees is equal to P, determine without the use of a calculator each of the following in terms of P. Okay, so sine 27 degrees is equal to P. So this is our trig diagram. That's where we're going to get our diagram from. 27 degrees would lie in the first quadrant because this is an angle that is less than 90 degrees. So we measure 27 degrees, okay, from 0 degrees. So that's 27 degrees. And they told us that this is equal to P. Okay, so this is the line drawn perpendicular to the x-axis. And we know that sine 27 degrees is equal to P. You see that sine, okay, from saw katoa is P over opposite over hypotenuse. So if sine 27 degrees is equal to P, the denominator here of P is just 1. So it means the hypotenuse is 1 and the opposite side is P. So all we have to find is this adjacent side. And we can find that it's just an x value. So we'll say, using Pythagoras, because it's a right angle triangle, we'll say x squared is equal to the hypotenuse squared, which is 1 squared, minus the other shorter side squared, p squared. And to solve, you see that we are on the positive part of the x-axis. So when you square root both hand sides, yes, we consider the positive and negative solution, but we're just going to take the positive because we are on the positive part of the x-axis. So it's square root, that is just going to be 1. And this stays p squared. It doesn't get square rooted because you have a term, okay, another term here. Okay, so know what x is. X is 1 minus p squared. And now we can find cos 27 degrees. So here's 27 degrees, and cos from SOHCAHTOA is adjacent over hypotenuse. So we're going to take the adjacent side. So the side next to this angle is the square root of 1 minus p squared, and that goes over the hypotenuse of 1, which you can see will just simplify to square root of 1 minus p squared. Okay, and that is our answer. Moving on to the next question. Question 5.2.2 says we need to find the value of sine squared 63 degrees. Now, the diagram we have is related to 27 degrees. So we can just relate everything to 27 degrees. How does 63 degrees relate to 27? Well, if you say 63 plus 27, you see that you're going to get 90 degrees. So they're using cofunctions here. Okay, so we need to just make sure that this is equal to 27 degrees, the angle. So we can rewrite this as sine squared. Okay, I'm going to write it as sine 63 degrees all squared. And then now sine 63 degrees can be written as sine 90 degrees minus 27 degrees, okay, all squared. And so using cofunctions, this inside the bracket simplifies to cos 27 degrees. And of course, it's still squared. So this is just cos squared 27 degrees. Okay, so we know that cos 27 degrees is square root of 1 minus p squared. So cos squared 27 degrees is simply all of this squared. And that breaks open that root, and we have 1 minus p squared, and that is our answer. Okay, moving on to the next question. Question 5.2.3 says we need to find the value of cos 13.5 degrees. Now, how does this angle again relate to 27 degrees that we have in our diagram? Well, 13.5 is half of 27. So it means that if they're using half the angle, they're probably using double angles here. So we're going to have to think about double angle formulas that include cos 13.5. Okay, now straight away, if you try to use the one with sine, okay, like sine 2a equals 2 sine a cos a, remember that if this is 2a, we're looking at this as a, right? If this is 2a, that's 2 times 13.5. So yes, we would have sine 27 degrees. But then here you have 2 sine 13.5 degrees times cos 13.5 degrees. And with this equation, we can find the value. We already have the value of sine 27 degrees. But then we're trying to find cos 13.5 degrees. It would be a problem to use this equation because we have no idea what sine 13.5 degrees. Okay, we only know what sine 27 degrees is. So ensure that you use a double angle formula that would be able to solve for this. So the best formula to use in this case, or one of the ones that you can use, actually it's the only one in this case, would be cos 2a is equal to 2 cos squared a minus 1. Okay, and this is because it includes a, which we are calling 13.5. So in place of a, we could just say 13.5 degrees. And in place of 2a, we can just say this is 2 times 13.5, which is 27 degrees. So this is 27 degrees. And this is perfect to use. Okay, so with this equation, all we're going to try to do is make cos 13.5 the subject because we have a value for cos 27 degrees, and this is just 1, and that's just 2. Okay, so cos 27 degrees, that was the square root of 1 minus p squared. Okay, so that is root 1 minus p squared is equal to, and we have 2 cos squared, might as well transpose this 1 now. So it's now plus 1 here, is equal to 2 cos squared 13.5 degrees. And then divide both hand sides of the equation by 2. And what we have now is cos squared 13.5 degrees is equal to, and here we just have the square root of 1 minus p squared plus 1 over 2. And then finally, to solve, we'll say that to solve for cos 13.5, we can square root both hand sides to get rid of that square. Okay, again, positive and negative, but we see which quadrant we're in. Okay, 13.5. That's where those x and y values are positive. Okay, so we're simply saying that cos 13.5 degrees, that this is simply equal to the square root of 1 minus p squared plus 1 all over 2. And that is our answer. Okay, moving on to the next question. Question 5.3 says, if cos x plus sin x is equal to k, express the following in terms of k. And they want us to express cos x minus 45 degrees. Okay, very possible because we have a special angle and we have cos. So we can use the compound angle rule for cos to expand this first. So this will be equal to, we have cos x multiplied by cos 45 degrees, and then the sign will change to plus, and then sin x multiplied by sine 45 degrees. Okay, so this is equal to, now you have a choice here. You see cos 45 degrees and sine 45 degrees. Okay, now you see with cos 45 degrees and sine 45 degrees, notice the angle is exactly the same. So they are also cofunctions. They will be equal to the same thing. Now, it depends on what you use. If you use the calculator, you're going to get that cos 45 degrees is equal to the square root of 2 over 2, where the denominator is a rational number. If you don't use the calculator, you're going to get 1 over root 2. Okay, so we'll just keep that in mind. This is with a calculator and this is with no calculator. So let's try it first without the calculator. So this would be cos x multiplied by 1 over the square root of 2 plus sin x multiplied by 1 over the square root of 2. And then you see that they are common in both terms that we have. So we can simply take this out as a common factor. We have 1 over square root 2 out as a common factor, and we are left with cos x. And then in the second term, we are left with positive sin x. And there we go. There's our cos x plus sin x. And we know that that is equal to k. So this would be, so it could either look like this, or let's also just make it look like this one. So it could be root 2 over 2 times, cos x plus sin x. So in this case, it would be, I'll just write it in the next line. This is 1 over root 2 multiplied by k. So that is the k value they were referring to. Or it could be root 2 over 2 multiplied by k. These are the same values, okay? Just one has a rational denominator, the other has an irrational denominator. So in this case, when you multiply the numerators, this would be k over root 2. Or it could be written as root 2 k over 2. So there we go. Okay, if you decided not to write the k in the numerator, you could have just written it as root 2 over 2 k. And here that would be 1 over root 2 k. So either answer would be fine. You can write it like that or like that. And that is it for this question. Moving on to the next question. Question 5.4 says, prove the identity, and we have cos 2 theta plus 1. Okay, we can already see the left-hand side is what we're working with here. So say left-hand side equals and rewrite. Okay, so we're just trying to get this to look like this right-hand side. And let's evaluate. You see, with this cos 2 theta plus 1, I'll hold on to that. Let's see the denominator, right? It doesn't really have any other choice but to change to one other thing, which is 2 sine theta cos theta. So with this, the only choice that we have now is we can make this or ensure that this ends up being one single term. Okay, we've got cos 2 theta, which is double angles again, just like with the denominator. But we have a plus 1. As long as this plus 1 is here, you're going to always have more than one term. So let's ensure that we change it to something that can cancel out this positive 1. So we need to remove a positive 1, meaning change it to a double angle identity that includes minus 1. So that means we can change it to this double angle identity, which is 2 cos squared theta minus 1, and then we still have that plus 1. And you see how they will simplify to 0. And then we have tan. Okay, there's no tan here, so you know you need to change this to sine theta over cos theta. And this is equal to, and okay, so these ones, they simplify, they cancel. And what will happen here when they become 0 is the 2 will divide by 2 to give you 1. And one of the cos theta here will cancel with this. So all we're left with here is cos theta over sine theta, and then plus sine theta over cos theta. Okay, it makes sense. That's how they got that denominator. So we need to add these fractions. But to add fractions, the denominators need to be the same. So we can write the common denominator. The LCD will be, because this is sine theta and this is cos theta, the only way they can be the same is as sine theta cos theta. So we will look at each term and ask ourselves, what did you multiply to this denominator so that you can get this as a denominator? We multiply by cos theta. So you must have multiplied the denominator and the numerator by cos theta, meaning this numerator will be cos theta times cos theta, which gives us cos squared theta. Okay, same thing over here. We'll look at this fraction, look at the denominator. What did we multiply to this denominator to get to this? You must have multiplied by sine theta. So you multiply the denominator and the numerator by sine theta, meaning this numerator will become sine squared theta. So that's plus sine squared theta. And there we go. You see that is the identity for 1, okay? Sine squared theta plus cos squared theta is equal to 1. And the denominator stays sine theta cos theta. So there we go. That is equal to the right-hand side. So we can say it's equal to the right-hand side, and we have proven this identity. Moving on to the next question. Question 5.5 says, determine the general solution of the equation. So this is the equation we have, and let's just rewrite it. So we have 4 sine squared theta, and you can see they're using cofunctions here. Okay, we can just simplify at this point. Okay, so I've rewritten it, and now this is going to become a sine. We will need to take it over at some point, but it's fine. Okay, and I'll tell you why I'm saying we'll need to take it over. So here's the thing. This becomes positive sine 2 theta using cofunctions. And then you see that we have 4 sine squared theta is equal to, and sine 2 theta expands to 2 sine theta multiplied by cos theta. This is the identity. Now, I know that at this point, it can be very tempting to say, let's just divide both hand sides by sine theta. Do not do this, okay? Because you don't know what sine theta is. It's kind of like with equations when solving for x. You can't start dividing by x when we have no idea what x is. Because if x is equal to 0, then you have yourself an undefined equation. And you don't want to do that. So what we're going to do is we're going to transpose that. And now we have 4 sine squared theta minus 2 sine theta cos theta. So the danger here with dividing is if sine theta happens to be equal to 0, your equation is going to be undefined. Okay, so then it's not going to make sense. So now with this, we can go ahead and take sine theta out as a common factor. And well, it's not just sine theta. See, the common factor between these two terms would be 2 sine theta, because 2 is common between 4 and 2. So this is 2 sine theta, open a bracket. What is left here? That's 2 sine theta. And then what is left here? That's minus cos theta is equal to 0. And now we have a factor times another factor give you 0. It's either that the first is equal to 0 or the second is equal to 0, just like with trinomials as well. So this is equal to 0. If you equate it to 0, you would have to transpose this negative cos theta, so it becomes positive cos theta. Okay, and here if you divide both hand sides by 2, sine theta is finally equal to 0. Okay, and then here we can form tan, because you see we have sine theta, cos theta. Tan theta equals sine theta over cos theta. So we could divide both hand sides by cos theta so that we can form tan theta. Now, because this should stay tan theta, we need to get rid of the 2. So you should also divide both hand sides of this equation by 2 as well. So now we have tan theta is equal to, cos and cos cancel here, and we have 1 as an invisible 1 there. So that's 1 over 2. Okay, so these are our two equations, and we just need to solve for theta and find the general solution. So with this, you can choose to use any method you're comfortable with, either using the cos diagram or using the sine graph itself. Okay, so we're just working with these two equations, and we just need to solve for theta. Okay, it's just sine and tan, and you can see that the values they are equal to are both non-negative values. Okay, so if you were using the cos diagram with this one where it's equal to 0, you're going to look for places where sine is not negative. Okay, and sine is not negative in the first and the second quadrant. So we'll use those reductions. So this one is 180 minus theta. And so we would say to solve for theta, well, we need to first find the reference angle. The reference angle here would just be 0 degrees. Okay, if you say shift sine of 0, you get 0. So that is just 0 degrees, and we'll say theta is finally equal to, and the first reduction, that will be 0 degrees plus k 360 degrees. You can also just simplify this to k 360 degrees, just meaning whatever value you substitute for k, whatever integer value would result in a solution for this equation. Okay, or we can say theta is equal to 180 degrees minus 0 degrees, which is just 180 degrees, plus k 360 degrees, and you need to include that k is an element of integers. You can only substitute integer values here. And that will be the answer to that. And now let's go ahead and take this equation. Okay, so here's the other one we have. So I'll just say, oh, we have this as well. And tan theta is equal to a half. A half, well, that's not the value that I know it's like a half and it looks like, yeah, we could find a special angle here. So a half is not one of those special angles. So we actually have to find the reference angle here. It's not one of those simple ones that we can find. So we'll say arctan of a half. Okay, shift tan a half, and you see what we get. Now at this point, you are safe to round off, no problem. It's not going to affect your answer. So this is 26.57 degrees. Great. We're going to use that. And now we can finally solve for theta. And this is the reason I don't like to use the cos diagram when solving for general solutions. I feel like it complicates things. You see, if you learn what your graphs look like, it becomes very easy. So with the sine graph, all you needed to do is draw the sine graph. You know what it looks like, where sine theta equal to 0. It's equal to 0 at 0 degrees and at 180 degrees. Done. Of course at 360 degrees, but that's just a repetition of what's going on here, okay? And then with that, you would have said, okay, it's at 0 degrees plus k360 and 180 degrees plus k360. Done. And then with the tan graph, this would also simplify things a lot. You're saying, where is my tan graph equal to a half? Where does it have a y value of a half? It has a y value of a half like this. You need to remember what it looks like. So remember that there's an asymptote at 90 degrees, and then the graph goes up, and then it goes like that. Okay. And so where it's equal to a half is here, where we found the reference angle, okay, at 26.57 degrees. So it's equal to a half here, but this is a tan graph, okay? This ends at 180 degrees. One cycle is completed within 180 degrees. So it repeats itself every 180 degrees. You see this answer again, okay, where the y values are half. It's going to repeat itself 180 degrees later. So you wouldn't have to now take two solutions. if you use the cast diagram, you would have two solutions which are just a repeat of each other. And that's why I don't like to use this too much, because there's too much repetition that can happen sometimes. So with this, because of the way the tan graph looks, I'm simply going to say that theta is equal to, and my answer here is 26.57 degrees, and plus k of the tan graph repeats itself every 180 degrees. So plus k of 180 degrees, where k is an element of integers. These would be your answers: 1, 2, and 3. And that is it for this question, and that is it for question 5. Question 6 says, in the diagram below, f of x is equal to a sine bx and g of x equals 4 cos x are drawn for the interval x is an element of negative 180 degrees to 180 degrees. And the graph of f of x passes through 90 degrees and 5. Okay, they're giving you these special points just so that you can see what exactly this graph is going to look like. Okay, the value of a and b. And they say the graph of g passes through 90 degrees and 0. A and b are points of intersection of both graphs f and g, and a is this point over here. Okay, great. They gave us 1 point of intersection. And the first question is to determine the values of a and b. So a and b, that refers to the graph of f. So you see with f of x, it's a sine graph. And let's look at this sine graph. I'm just going to highlight it. And let's compare it to what the original sine graph looks like so that we can understand what they have done to this graph. The original sine graph, right, is this graph, sine of x, where the graph goes to a highest of 1 and the minimum it reaches is negative 1. Now, this is, of course, from 0 degrees to 360 degrees. If you had to extend this, right, till negative 180 degrees, you'll see half of the graph here as well, okay, and also reach a minimum of negative 1 at this point. So that's actually the graph we have here. It is going from 0 degrees, okay, to 180 degrees, then that's where it hits the x-axis, and then it will continue there. But we can't see that because this has been cut within this interval. Okay, so what is the value of a? A tells you how high your graph really goes. Okay, it just shows you from the midline how high your graph goes. The original sine graph from the middle, right, it goes to a height of 1. And then, of course, it does the same thing downwards as well to go to the lowest of 1, okay, 1 units below. But with this one, from 90 degrees, because we know at 90 degrees, sine 90 degrees is naturally 1, but it's now 5 here. Now, you need to verify this by checking negative 90 degrees. Do you see that sine negative 90 degrees here is negative 5? So this graph, the value here that has been added is 5, okay, so that it reaches a height of 5 and then the lowest of negative 5. So we know that A is simply equal to 5. And what is B? So B is over here. So this is the value that will tamper with the period of your graph. Let's look at the period. The period of a sine graph, okay, y equals sine x, is 360 degrees. It completes a cycle within 360 degrees. Is this one completing a cycle within 360 degrees? Yes, it is, okay? From 0 to 180 degrees, we have half the graph. So the other half, the graph will be from 180 to 360. We can see this is a full sine graph, okay? So it does complete a cycle within 360 degrees, meaning they haven't really changed the value of b. So we can simply say that b is equal to 1 because you just said 1 times x. So it's just 5 sine x, okay? That has not been tampered with. So the value of b and b is simply equal to 1. And that is our answer. Moving on to the next question. Question 6.3 says, the graph of g of x is shifted 30 degrees to the right and 2 units vertically down to form the graph of h. Determine the equation of h. Okay, let's just understand the translation that happens here. We have a new equation, h of x, and it is formed by taking the graph of g and shifting it 30 degrees to the right. So if it moved to the right, that means we are going to subtract from the x. Left and right movements affect x, okay? And then up and down movements affect y. Okay, as you can see, that's up and down, that's the y-axis. Left and right, that's the x-axis. Okay, that's the movement that we'll see. So here, by g of x, you see wherever you see x, we're going to subtract 30 degrees to show that this has been shifted 30 degrees to the right. And then they say 2 units vertically down. If you shift the graph up or down, it affects the y value, meaning the y value of this graph, all the y values will move down by 2 units. Now, when you're moving down, it's simply minus and up is plus. Very simple with that. But with the x and y, with left and right movements, okay, if you're moving to the right, when you're applying this to the equation, you say minus whatever value it moved to the right by. And then left would be plus whatever value that is. So this is going to be minus 2. But you see, we're saying y minus 2. Right now, what represents why the y values of this graph so long, with the only translation that has happened, is this. This represents the y values. Once you apply this, it will give you the new equation of h. So we're taking this as the y values and we're going to say minus 2. Okay, so this is a mathematical explanation of what just happened. And now we actually have to apply this. Okay, let's take our graph of g. So g is 4 cos x. So we're saying h of x is equal to 4 cos, and wherever you see x, you're just going to replace this as x minus 30 degrees. You subtract 30 degrees from it. Now this y value, we're going to take this and subtract it by 2. Okay, and that's how we apply it in here. And that is the equation of h. You don't have to... we don't have to expand that. So it's 4 cos x minus 30 degrees minus 2. Moving on to the next question. Question 6.3 says, calculate the minimum value of this expression 8 over g of x, okay, in the interval where x is an element of negative 60 degrees to 60 degrees. Okay, see, there's one thing we need to note here. Had this been g of x divided by 8, it would work a different way. But they say 8 divided by g of x. The expression we are focused on is this, 8 over g of x. It needs to be the lowest that it can be. So what should g of x be to ensure that this expression is at the lowest possible value that it can be? So think about the kind of numbers we can divide this by. Let's say we said 8 divided by, and I'm just going to compare it between two numbers, right? If we said 8 divided by, let's say 4 versus 8 divided by 1, which gives you a lower value? It would be 8 divided by 4, which is 2. This gives you 8. But notice, look at these two numbers. Which is bigger? The 4 is bigger. So because we're saying 8 divided by a number, we need to ensure that this value that we choose here is the highest value that g of x can be. Because if you take 8 and you divide it by the highest value you can divide it by, it's going to ultimately make this expression as small as it can be. So the minimum value of this expression will occur where g of x is a maximum, okay, is at its maximum value, of course, within this interval. So this was just a case with numbers. Okay, when you divide by these things, you need to think about the full picture. The full picture is the 8 over g of x. That's the expression they want us to find the minimum value of. Okay, so let's go ahead and look here. We have from 60 degrees, from negative 60 degrees to 60 degrees. We look at the graph of g. So it's within this interval, and this is our graph. So we need to ensure that we pick the highest that this graph reaches within this interval. The highest that the graph of g, this cos graph, reaches is 4. So we'll say 8 divided by 4. So the maximum is at 4, max at where g of x is equal to 4 within that interval. So 8 divided by 4, and then the minimum value of this expression becomes 2. And that is the minimum value of this expression. Okay, so you can look at this and see what would have happened if you chose the minimum value. If you said, okay, we're going to say 8 divided by the lowest that g of x can reach. if you say 8 divided by this lowest that it reaches here, which is 2, you would have said 8 divided by 2, which is 4. And 4 is a bigger value than 2. So clearly this is not the lowest it reaches. Okay, so you have to think about that and just think about how numbers work when you are dividing by this y value. Okay, so we're taking 8 and dividing it by that. So you can just conclude that the minimum value is 2. Okay, the minimum value of this expression, 8 over g of x, is 2. Moving on to the next question. Question 6.4 says, if a is negative 141.34 degrees, and okay, so it's that same point they gave us of a, they want us to determine the coordinates of b, so the other point of intersection. Okay, let's look at our graph. So this is our graph. This is the first point of intersection we have. And then they want us to use this to find out exactly what b is. Okay, so with these graphs, you need to learn how to see the symmetry with the graphs. You see the sine graph. Okay, and I'll focus on the sine graph because it's actually easier to spot this on the sine graph right now. It seems easier. So you see with the sine graph, what the sine graph does over here, it does the exact same thing over here. Okay, you see why it reaches a maximum of 1 here. Okay, it's like a parabola. It's like a concave down parabola and a concave up parabola that you can look at it as. So if it reaches the highest of, it's reaching 5, of course, because that a value was changed to 5. So if it reaches the highest of 5 here, and here it reaches the lowest of negative 5, they are symmetrical. So you could pick this one up, and if you turned it around and then you just put it on here, it will fit perfectly on here. Now, I'm going to use their symmetry to find this point B because there's no way they want us to deal with like general solution. This is only for 2 marks. So I'm just simply going to use their symmetry. Okay, so think about this. We're trying to find out, okay, what this point, this intersection is going to be. Okay, so the y and the x value. Okay, and I just drew yellow boxes around it so you can see this better. You see, this is really just a repeat of what this looks like. If you pick this up and you flipped it around, it would sit perfectly on this. So that means that we went from negative 180 degrees and we went how many degrees to the right so that we could reach this angle, negative 141.34 degrees, and a y value of negative 3.12. So to find that, we can simply say 180 degrees minus 141.34. So we can just see how many degrees to the right do we move so that we can reach this point of intersection. And that is, we went 38 degrees, 38.66 degrees to the right. Okay, so if this is how much to the right we went, then you see this graph, it does the exact same thing. It would also be, okay, from where this graph has a y value of 0, you would also move 38 degrees, 38.66 degrees to the right. Okay, so at 38.66 degrees to the right, we would reach a y value of, now you see here, from this point, we reach this y value of negative 3.12. So what is that going to look like on this part? If we went to negative 3.12 to reach this point of intersection, then here, this would be at positive 3.12. So the graph does the exact same thing that it does over here as well. Okay, so if you look at this little rectangle, it's going to be the exact same length and height as well. Okay, if I just drew it like that. So we know that we just go from 0 to 38.66, and then this point of intersection will be at 3.12. Okay, and that is what B is going to be. Okay, so I've just screenshotted this and pinned this to the screen just so that you can see what's going on. I just resize this. Okay, so you see how it fits perfectly like this. Okay, like this. So this graph does the exact same thing. That's why it's going to reach a height of 3.12 and then at that x value. Okay, if I had to like turn that around, you see how that fits perfectly, and now it completes the image of the sine graph that we had. This sine graph is symmetrical, so That's how we could easily find that instead of going through a long method. So B is simply 38.66 degrees, and the y value is 3.12 as a y value, not degrees. And that is our answer. Moving on to the next question. Question 6.5 says, for what values of k will f of x equals k have no real solutions? Okay, where will it not have any real solutions? Well, you can just look at what the graph of f looks like. That is the sine graph. Remember that it reaches a height of 5, and then the lowest it reaches is -5. Okay, so let me just remove these. Okay, so that would mean the only places that it's not going to have any solutions for f of x is equal to k. Okay, so you need to think about, since we're saying f of x is equal to k, which y values will it never have solutions for? It has solutions. Think about all the y values it has solutions for. It has solutions for y values that are greater than -5, but less than 5. If you go anything beyond this, the graph will never intersect there. Okay, so the graph will not have any y value. There's no graph up here above 5, and there's no graph below 5. Okay, so it will not have any of those y values. So we can simply say that k would be greater than 5, or let's just start with the less than. So it will not have any solutions where k is less than -5, or where k is greater than 5. And that is our answer. Moving on to the next question. Question 6.6 says, use the graphs to determine the values of x in the interval where we're going from -180 to 180, for which f of x is less than g of x. Okay, so it's just our graph as it is. So where is f of x less than g of x? Now, these refer to the y values. So we need to look for places where the y values of f are less than g. In other words, g needs to be above f, because the places where g is above f, for example, here's our graph of g. Okay, here, the graph of g is below the graph of f. So here, g has a lower y value than the graph of f. So we'll have to keep moving to the right and just see where this happens. Now, what would help here is finding those points of intersection, because after the point of intersection, you have one graph above the other, or the other being above that one. So here we could see that this doesn't happen here. Okay, the graph of f is above g. But over here, now you see that the graph of f is now below the graph of g. Okay, so the graph of f is below the graph of g all through until the next point of intersection. And we know what that x value is now. Okay, remember that this is 38.66 degrees. So it happens all through here. We can see that now, where x is greater than -41.34 degrees, but x is less than 38.66 degrees. So it happens all through here. Okay, this is where the graph of f is below the graph of g. And then here you see that the graph of f now goes above the graph of g, and that's not what we want. We want f to be below g. Okay, the inequality is facing the g, meaning this is the bigger one. So this must be above it. Okay, so that is between these two values, and we'll just tell them this is where x is greater than that -141.34 degrees, okay, 0.34, but x is less than 38.66 degrees, and that is our answer. Question 6.6.2, the last question for question 6 says, we need to find out the values of x for which f prime of x multiplied by g of x is greater than or equal to 0. Okay, when you see f prime of x, and you know we're working with trig, don't get afraid. All they're saying is, if we have f prime of x, this is actually referring to the gradient of this graph. When a gradient is positive, it means that this graph will be increasing. If you read it from left to right, it's moving up. When the gradient is negative, the graph will be decreasing. So we need to find out For which values of x will the gradient of the graph of f multiplied by the y values of the graph of g be greater than or equal to 0? Okay, let's look at the possibilities. So we need to still get a number that is either greater than or equal to 0. So if this is positive, so that will be where the graph of f is increasing, and we multiply it by this, and this is also positive, then we get a positive value. That is a value greater than 0. And if this is negative, and we multiply it by a negative, then we get a value that is also positive, a value greater than 0. So we're really just looking for the places where the graph of f is increasing, and at the same time, the graph of g has positive y values. Okay, so I'm going to pin this, and let's just go ahead and look and see if we have these. Okay, looking at our graph, we need to, it's best to actually just point out this first. So it will be easier to work with f prime of x first, because f prime of x is just telling us where the graph is increasing or decreasing, when it's positive or negative. So looking at the graph of f, okay, this is our graph of f. Where does it have a positive gradient? This will be where it's increasing. So look at what the graph is doing. Here, if you read from left to right, it is decreasing here, and then it starts to increase. And then after it reaches that maximum, it decreases. Okay, so we can see the places now that it is decreasing and where it is increasing. So decreasing all through here and increasing. Now, we want to find where it is increasing, and for the same x values, the graph of g's y values are positive. Let's look at the graph of g. Where does the graph of g have positive y values? The graph of g has positive y values when it is above the x-axis. If you map all of these points to the x-axis, you see that they correspond to positive y values. All of these are positive values. When you go below the x-axis, this is where it has negative y values. So this is what we're looking for. We want the graph of g to have positive y values and the graph of f to be increasing. And do you see where this happens? It is, let me just erase that, it's within this region. So from negative 90 all the way to here, okay, all the highlighted sections. Now, remember they did say greater than or equal to 0, okay? So we can also include this. So greater than or equal to 0, we can actually include negative 90 and 90 degrees, because at negative 90, then we see that here the y value is 0. But here, this is a turning point. The gradient is also 0. So 0 times 0 is still 0. Okay, so it would be those points as well. And the first solution that we have so far is where x is greater than or equal to negative 90 degrees, but less than or equal to 90 degrees. Okay, great. So we've got that part. So this part is settled. We know that this actually does happen on our graph. Now let's look at this part. Here, the graph of f should be decreasing. So let's highlight where it's decreasing. Remember that was here. It was moving down, okay, reading from left to right. And it was also here. It's moving down. Now, for the same x values, the graph of g should have negative y values. Okay, where does the graph of g have negative y values? All through here, where it's below the x-axis. Okay, and here again, it's below the x-axis, has negative y values. So it seems like it just works everywhere. Okay, if we mark from here and we look at that, the interval in which it works is from negative 180 degrees to negative 90 degrees. And also here, you see that it's also from 90 degrees to positive 180 degrees. Okay, but you just need to make sure that you see what's going on this side, okay? Whether we can actually include negative 180 degrees and 180 degrees. Remember that we're referring to f prime of x, okay? So the gradient of this graph of f. The gradient of f, the sine graph at this point, is not 0, okay? Because when we look at what that graph is doing, if we continued it, it would still be moving down. Okay, it's only at the turning point, that's where the gradient is 0. So if the gradient of f was not 0, okay, but a negative value because it was moving down, and as you can see, the value of g there is negative. It's a negative y value, okay, of that like negative 4 there. And so if you multiply those, negative multiplied by negative, you still get a positive. So because you also get a positive value there, we'll also say negative 180 degrees is included here. And likewise with this part, this point over here. With this point, again, the graph of f, its gradient, you can see the graph is moving down, okay? So that's a negative gradient, it's decreasing. So the gradient there is negative, and the y value of g is also negative. So when they multiply, they give a positive because they give us a positive value which meets one of the criteria that we're looking for, greater than or equal to 0. Okay, that's greater than 0. Then we're also going to include 180 degrees. And so we see that it meets this criteria all through. So it means that it works for everything, okay, the entire domain that they gave us. So we can finally just tell them the answer can be left like that. And we can finally just tell them that this means that x is greater than or equal to negative 180 degrees, but less than or equal to 180 degrees. Again, this can be written as x is an element of negative 180 degrees to 180 degrees, and ensure that you use square brackets to show that these are included x values. And that will be our answer. So you can leave it like that or like that. And that is it for question 6. Question 7 says, in the diagram below, TQR represents 3 points in a horizontal plane on a sports field. Okay, so this is the ground. And then they say that PQ represents a vertical flagpole. The angle of elevation of the top of the pole from R is theta. And angle T is equal to theta. TQ is equal to TR, and they're both equal to Y. And QR is equal to X units. And lastly, we are given that TQR is alpha. And we need to express theta in terms of alpha and then show that sine theta is equal to sine 2 alpha. Okay, so the main goal is you need to express theta in terms of alpha. Because they're asking for specifically angles, let's actually just look at those angles. We have theta here, but then there's no alpha in this triangle, in this right angle triangle. We only can relate it using trig ratios, and they specifically want angles. So let's actually just focus on the angles. Let's look at this triangle over here. In this triangle, we have theta. We also have alpha. But remember, it's an isosceles triangle. So we can express theta in terms of alpha here. So this is opposite y, meaning this one, because it's also y, this angle over here in this triangle on the ground is going to be alpha. Okay, so just remember that this is now alpha. So let's just say that as well. Let's state it. So we can see that this angle TRQ is equal to alpha. Now we have to express theta in terms of alpha. So you see how they are inside a triangle, so they would add up to 180 degrees. So we can say that, we can see that in this triangle, you don't really need to say these things, but I'm just going to keep this in mind. In triangle TQR, we can take theta plus alpha, and they give us 180 degrees. And we just need to express theta in terms of alpha. So make theta the subject. So theta is equal to, so we'll say theta, these together give us 2 alpha. So this is 180 degrees minus 2 alpha. Okay. So if this is 180 degrees minus 2 alpha, we have expressed theta in terms of alpha, like that. But now they want us to also show them that sine theta equals sine 2 alpha. Why does this feel a lot for 2 marks? Okay, it's probably because it's probably not that deep, really, because they're saying sine theta and 2 alpha. Well, we have theta here and we have alpha, and we know, yeah, you see with 180 degrees minus alpha, remember from your cos diagram, okay, in sine's quadrant, this is where we have 180 degrees minus theta, this reduction. Let me just call it x, okay, to avoid any confusion. So they just have sine theta and then sine 2 alpha. We know that this, if sine is applied to it, it can reduce to 2 alpha. So that's what they did, okay? So they said if theta is equal to 180 degrees minus 2 alpha, then sine of theta would also be equal to sine of 180 degrees minus 2 alpha. Okay, so now we can finally just simplify this. Okay, using the reduction, you see that this will simplify to alpha. Okay, so this is simply just sine theta is equal to sine 2 alpha. And there we go. So they asked for those two things, and that is our answer. Moving on to the next question. Question 7.2 says, hence prove that in triangle PQR, that PR is equal to this. Okay, so it includes y, cos alpha, and cos theta. Okay, so we have this triangle in triangle PQR. So I'm going to just deselect that. Let's select this triangle here. The whole point is they're just finding the length or an expression for PR. So PR is the hypotenuse. Well, in this triangle, the only thing we can relate it to is this theta that we have. So, and we also have x. Okay, so we can say we have theta and then x is the adjacent side and then PR is the hypotenuse. So clearly we need to use cos here. Okay, so we're saying cos of theta equals x over PR. Okay, so cos theta equals x over PR. And then PR needs to be the subject. So let's already make it the subject. And so if you transpose it, if you multiply both hand sides by PR, you get PR cos theta equals x. And if you divide both hand sides by cos theta, you get PR equals x over cos theta. Okay, so this is PR as a subject. How did they get it to look like this? Okay, so the first thing we see is the denominator is fine. It's just that numerator. So 2y cos alpha, that was clearly what x was. So we need to just find out what x is. So let's look. How do we find x? Okay, we can find x using this diagram. Okay, the triangle below here. So in this triangle QTR or RQT, to find x, this shouldn't be a problem. We can use the sine rule. So we can say we're trying to find x, so we're going to use the angle opposite x. And then with these ones, we already know their angles. It's alpha and y. Okay, so we can say x over sine theta is equal to y over sine alpha. Okay, so with this, we're saying x over sine theta is equal to y over sine alpha. And that is in that triangle RQT. I'll just say in triangle RQT, just in case, something does not work out, we can backtrack. Okay, and now I'm just going to make x the subject because I need to find out what exactly x is, somehow equal to this, clearly. And then substitute it there so that we can finally find what PR is equal to. Okay, make x the subject. Just multiply both hand sides by sine theta. Therefore, x is equal to y sine theta over sine alpha. And it doesn't look like it yet, but let's just substitute it in. So PR is equal to, and we have x as the numerator. This is this. So we're saying y sine theta over sine alpha, and we're dividing by cos theta, which is, cos theta. Okay, it's the same thing as saying over 1, and then you can tip and times. So you're going to swap the numerator and denominator. So this is cos theta, and the numerator is 1. And then you change this to a multiplication sign. So we have PR is equal to, when we multiply, we have y sine theta over sine alpha cos theta. Let's just compare. How does it look compared to this? Okay, let's just see what it doesn't include. It includes cos theta, right? It has y, and then this 2 is not there, and of course everything else. So I'm just going to separate them so I can just make sense of this. So I'll leave this as y over cos theta, because that seems fine. And then I'll separate this. So multiply by that numerator is sine theta, and the denominator is sine alpha. And I just want to understand why they had this, eventually equal this. Okay, now looking at sine theta and alpha, yeah, it has to do with this. You see how sine theta is equal to sine 2 alpha, okay? So we need to make sure that we still have a cos alpha. Okay, so this is what they did. In place of sine theta, because sine theta was equal to sine 2 alpha, they replaced it with that. So I'm just going to say, but we knew already that sine theta was equal to sine 2 alpha. And in place of sine theta, let's substitute. So PR is equal to Y, and we have sine 2 alpha over, and we have cos here, and then I think I should have still left it as separate angles. Here's why. Because if I say y over cos theta, and I say multiply by, and this changes to sine 2 alpha over sine alpha, then we can use double angles to expand this. So we're saying PR is equal to y over cos theta multiplied by, and then this becomes 2 sine alpha cos alpha all over sine alpha. And then you see how these cancel, and that's where the 2 came from. So finally, it means that PR is finally equal to, we're going to say y times 2 cos alpha. So that's 2y cos alpha all over, and the only denominator left is cos theta. And there we go. So that's how it's equal to this. And moving on to the next question. Question 7.3 says, if alpha equals 49 degrees, x equals 20 meters, y equals 15 meters, calculate the area of triangle TQR. Okay, so it's that triangle we just worked with, this triangle. But let's just take down what they've given us so we don't have to find any unnecessary things. So they gave us alpha, they gave us x and y. Okay, so find the area of this triangle. Okay, using alpha, x and y, okay, we can just look at it like this. Using alpha, it's going to be this angle over here, okay, in this triangle, and then x and y. We could just focus on that. So we would have to use the area rule because we don't have any perpendicular heights here. So the area of this triangle would be a half multiplied by the adjacent side, the side adjacent this angle, the center angle that we have here. So that's y times x and then sine of that center angle, which is alpha. So that's how it looks. Okay. So we're just going to substitute. So it's a half multiplied by 15 multiplied by 20 and then sine 49 degrees. Okay, and let's find the area. And the area of this triangle, okay, is 113 points, and that's going to round up to 21. Okay, and what was the unit of measurement? They said units, okay, x unit. So we're going to say it's this and then units squared. And that is our answer. Okay, and that is it for question 7. Question 8 says, in the diagram below, O is the center of the circle. A, B, and D are points on the circle. BC is a tangent to the circle at B, and angle DBC is 22.5 degrees. Chord AD is produced to C such that CD is equal to BD. And 8.1 says determine given reasons the size of, and the first angle we need to find is the size of angle A1. Okay, so looking at where A1 is, it's at the circumference, and we can see that it's supported by this chord BD. Now, we also have a tangent, so we have an angle between the tangent and the chord, and so it's going to be equal to the angle at the circumference, which is supported by that same chord. Okay, so it means that angle A1 is also equal to 22.5 degrees, and we can go ahead and tell them that. So angle A1 equals 22.5 degrees, and the reason is because of the tan chord theorem. And that is our answer. Moving on to the next question. The next question, 8.1.2, says we need to find the size of angle D1. Okay, so angle D1 is over here. How do we find that? Well, we've got this chord AB. It's not really helpful right now. Yes, it's supporting angle D1 at the circumference and angle O1 at the center, but we don't have angle O1, so we can't really go with that. How else can we find this? What is D1 in relation to the other angles around it? Okay, so do you see how this line is equal to this line? And so they form a triangle, and angle D1 is the exterior angle of that triangle. So because these two are equal, it means that the angles opposite their equal sides will also be equal. So that means that angle C is also equal to 22.5 degrees. So let's just put that down. We already know that these two lines are equal. So I'll say that angle C is also equal to 22.5 degrees. And the reason for this is because we have angles opposite equal sides. Okay, angles opposite equal sides are equal. And now that those two are equal, angle D1 is the exterior angle of this triangle. So the exterior angle is equal to the sum of the two opposite interior angles. So we'll know that angle D1 will be found by saying angle C plus angle B, which we can just call 22.5. That's fine. So we can just say it's 22.5 plus angle C, which is also 22.5. And this is because of the exterior angle of a triangle. So it means that angle D1 is 22.5 plus 22.5 degrees. And so it is finally equal to 45 degrees. Okay, and that is our answer. Don't forget to make sure that you write it in so that it can help us with the next question. Okay, moving on to the next question. And then 8.1.3 says we need to find the size of angle B2. Okay, angle B2 is over here. Straight away, I see that it's next to the tangent, the angle between the tangent and the chord. So you know that if we have a radius and we have a tangent, that they are perpendicular at their point of contact. So this forms a 90-degree angle, meaning to find angle B2, we can just say 90 degrees minus this available angle, and that will give us the size of angle B2. So angle B2 is equal to 90 degrees minus 22.5 degrees, and this is because the radius is always perpendicular to the tangent at the point of contact. And so therefore angle B2 is equal to, that'll be 45 plus 22.5, which is 67.5 degrees. Okay, and that is our answer. Moving on to the next question. Question 8.1.4 says we need to find the size of angle O1. Okay, I'm just going to put this down. Remember, we found this to be 67.5 degrees. And with all the information we have, how can we find O1? Okay, so O1 was already discussed in the beginning. You see how it's the angle at the center supported by this chord AB. And angle D1 is also the angle supported by this chord AB, but it's at the circumference. So the angle at the center is twice the size of the angle at the circumference as long as they're supported by the same chord or arc. Okay, so it means that angle O1, we can just say angle O1 is equal to twice the size of angle D1. And we'll put down the reason. Okay, and then angle O1 is equal to, that's 2 times 45 degrees, which is finally equal to 90 degrees. And that is our answer. Moving on to the next question. The next question, 8.2, says, prove given reasons that OA is parallel to CB. Okay, let's also just put that down. So this is 90 degrees. So we might as well just, do that. 90 degrees. So we need to prove that OA is parallel to CB. OA is parallel to CB. Okay, you can already see it now. But with proving that lines are parallel, you're going to specifically use Van angles. Well, Van angles is not the only thing that we can use. You have to use any theorem that speaks about parallel lines. And here's what I mean by this. Van angles says that if you find alternate angles on parallel lines, okay, that they are equal. If these lines are parallel and we find alternate angles, these angles are equal, okay? And if we find any other type of fun angle, like co-interior angles, okay, and they are on parallel lines, then it means they will add up to 180 degrees. And of course, corresponding angles would be equal, okay? So as long as they're on parallel lines. So for you to prove that lines are parallel, if you can find equal alternate angles, so they form a Z with the two lines that are said to be parallel, then it would mean that those lines really are parallel as long as those angles are equal. Okay, and in this case, as long as these two angles add up to 180 degrees. So with that being said, also just keep in mind that this would mean that you could also use the proportionality theorem. Of course, not in this case, but this is also a situation because the proportionality theorem speaks about parallel lines as well. Okay, so if we do find that these lines are in proportion, these sides are in proportion, then it would also mean that those lines are parallel. Okay, so that's really how to prove that lines are parallel. You need to stick with theorems that refer to parallel lines. So looking at this, straight away we can already see we have a Z, okay, with those two lines, and we can see those angles are equal. This is equal to this, therefore your lines are parallel. So that's what we can state. We can tell them angle O1 and angle, well, we'll call this OBC, that they are equal. So let's tell them angle O1 is equal to angle OBC, and they're both equal to 90 degrees. Since they are equal, it means that the lines that they lie on, those lines are parallel. So we can say that OA is therefore parallel to CB. Now the reason for this is, you see, we used alternate angles, but we can't say alternate angles on parallel lines are equal. So what we're really saying is because the alternate angles are equal, the lines are parallel. Okay, so I'm just going to say we have equal alternate angles, and that's fine. Even if you say alternate angles are equal, that's perfectly fine. Okay, and that is our answer. Moving on to the next question. Question 8.3 says, if it is further given that the radius of the circle is 12 units, calculate the length of BC. Okay, let's look at this. They told us the radius of the circle. Notice that we've got two radiuses, two radii here. We've got this and we've got that. Okay, so they're both 12 units. That's 12. That's 12. How can we use this to find BC? Okay, so looking at BC, we could try to use, we actually can't use the cos rule here either. It looked like we could use the cos rule, but we don't know what CD and DB are. Even if they're equal, we don't really know what they are, so that's not helpful. Using this triangle as well doesn't look like a good idea because I have no idea what this is. And also another thing is when they don't name certain points, okay, it's usually because that angle is not really useful for you to find what they need you to find. So I'm going to avoid that. Let's rather focus on what they gave us. They gave us the radius. How does that help with anything? So they gave us this is 12. We know this is also 12. And this is a right angled triangle. Okay. So if this is a right angled triangle, we can actually find this AB. But it's not good to find things that are not useful. Let's see how it would help. Okay. Do you see now we have another triangle here? This triangle ABC. Do you see that the angles are equal? Those two angles. This is an isosceles triangle, meaning their sides are equal. Okay, that is actually helpful. So if we find AB, we have found BC because this is an isosceles triangle. So let's go ahead and state that first. Tell them that AB is actually equal to BC because we have these two angles being equal. So AB equals BC. I have to state that first. AB is equal to BC. Now, the reason for that wouldn't really be angles opposite equal sides are equal, because this time we're not referring to the angles being equal. We're referring to the sides being equal. So it would be sides opposite equal angles are equal. Okay, so let's just say that, put our reason down. Okay, and now that we know the length of BC, we can simply just say, let's find AB. This is 12. This is 12. Let's use Pythagoras to find AB. So AB is the hypotenuse. It's opposite the 90-degree angle. So AB squared, so AB squared is equal to 12 squared plus 12 squared. And we are using the theorem of Pythagoras here. And that's 144 plus 144, which is 288. So AB squared is 288. And let's just find out what the square root of 288 is. So 288, 12 root 2. So AB is equal to 12 square root 2. Great. Now that we know what AB is, and we know that BC and AB are equal, we can simply just conclude, therefore this means that BC is also equal to 12 square root 2 units. And that is BC given the radius of the circle. Okay, and that is our answer. And that is it for question 8. Question 9 says, in the diagram below, the diameter BE of circle O is produced to D. DA is a tangent to the circle and CD is perpendicular to BD. AC and BC cut the circle at E and F respectively. OF and EF are drawn. Okay, so we've got a radius, we've got a diameter there. Okay, so the first question, 9.1 says, prove with reasons that ABCD is a cyclic chord. So ABCD is from A to B, and then C, and then D. Okay, so this is a cyclic chord. That's what we have to prove. Okay, immediately from the kind of lines that it has going across like this, you can see that the theorem that we can use to prove that it's a cyclic chord is that angles in the same segment theorem. So when you're trying to prove that a shape is something, or you're trying to prove that something is, for example, a tangent or lines are parallel, you have to use a theorem that specifically refers to that thing you're trying to prove. So if we want to prove that a shape is a cyclic chord, think about the theorems that mention cyclic chords. So here are the 3 theorems that refer to cyclic chords. So the first theorem is, if we can prove that the exterior angle of this chord is equal to the opposite interior angle, then this is a cyclic chord, okay? Because the exterior angle in a cyclic chord is equal to the opposite interior angle. Secondly, if we can prove that the opposite angles of this chord add up to 180 degrees, then the shape is a cyclic chord, okay? For the same reason, this is a theorem that refers specifically to a cyclic chord. The opposite angles of a cyclic chord are supplementary or add up to 180 degrees. And lastly, if we have the case where we have the angles in the same segment and they are equal, then this shape is a cyclic chord. So let's see what theorem we can use for this, depending on the kind of shape we have. You see how these lines go across? We already said we can use angles in the same segment. You could also use the exterior angle of a cyclic chord, okay? But angles in the same segment look more promising here. So if we can prove that this angle B1 is equal to angle C2, it's a cyclic chord. If we can also prove that angle A2 is equal to angle D2, it's a cyclic chord. And in the other ways as well, if you can prove that this is equal to this angle, it's a cyclic chord. And likewise, if you can prove that this angle is equal to this angle, it is a cyclic chord. Okay, but I'm going to go with the blue. And the reason why is because you see how that's 90 degrees? And you see how this is supported by a diameter? So straight away, we can already see that they are equal in that way. Okay, so this angle is actually going to be 90 degrees because it is supported by a diameter. It's the angle in a semicircle. So we can just tell them that angle A2 is equal to 90 degrees, and because it is the angle in a semicircle. And because of that, it means that it's equal to angle D2. So we can therefore say angle A2 is equal to angle D2. They're both equal to 90 degrees. And because of this, this proves that ABCD is indeed a cyclic chord. And the reason for this is because the angles in the same segment are equal. So it means that it's a cyclic chord. You can say that, or you could also say converse of angles in the same segment. And this is because we are not saying that this is a cyclic chord, therefore these angles are equal. We are saying these angles are equal, therefore this is a cyclic chord. Okay, so it's just the other way around. Okay, and that is it for this question. Moving on to the next question. Question 9.2 says, prove with reasons that BD bisects angle ABC. Okay, so just remember that if a line bisects an angle, to bisect just means to cut into two equal parts. So BD bisecting ABC, this larger angle, would simply mean that this means that we need to prove that angle B1 is equal to angle B2. Okay, so I'm not really saying they're equal yet. We just have to prove that they are equal. So we are required to prove that angle B1 is equal to angle B2. The reason it's good to write these required to prove is so that you don't lose focus and you don't lose track of what you're supposed to do and you don't end up finding things that are unnecessary. Okay, let's look at this. How can we show them that angle B1 is equal to angle B2? Well, it's clearly not a one-step process. It's 3 marks, so it's usually like 2 to 3 steps. Usually 2 steps. They wouldn't really give you 3 marks for a whole 3-step process. Sometimes they do though. Okay, so I'm also just going to keep in mind what we proved previously. This shape is a cyclic quad. So, because the shape is a cyclic quad, here's how we could focus on doing this. Okay, so using that this is a cyclic quad, how do we show them that these two angles are equal? Okay, so I don't want to say they're equal and get distracted. We just need to show that these two are the same. Do you see that angle B1 is at the circumference? So angle B1 is supported by this chord AE. So the angle between the tangent and that chord is equal to the angle at the circumference supported by that same chord. So angle A3 is equal to angle B1. Now, we can also see that since this is a cyclic quad, angle A3 is equal to angle B2 because of angles in the same segment. And so since both angles are equal to angle A3, they are equal. Okay, so there, it's a 2-step process in this case. So angle A3 is equal to angle B1. That's where we can start. Angle A3, or say angle B1 is equal to angle A3 because of the tan chord theorem. And then we can also show them that angle A3 is also equal to angle B2 because it's angles in the same segment in this cyclic quad that we have. So angle A3 equals angle B2, we'll just say angle B2 equals angle A3 because of angles in the same segment. And so because they're both equal to angle A3, it means that they are equal. So therefore angle B1 is equal to angle B2. And you see that we have proven what we were required to prove. And so because those two angles are equal, it concludes that BD indeed does bisect this angle ABC. Okay, because we can see that they are equal. And there we go. Okay, so just make sure you put down what is equal here because it will probably help you with the next question. So remember, angle B1 is equal to angle B2, and that is also equal to angle A3. Let's keep that in mind. Moving on to the next question. Question 9.3 says, prove with reasons that EC is a tangent to the circle at OEF. You are proving that something is a tangent. Therefore, you need to use theorems that relate to tangents. Well, there are 2 theorems. Okay, you can use, if it supports it, if the diagram supports it, of course, you can use this theorem that says that the radius is perpendicular to the tangent at the point of contact. So if you notice, hey, this is 90 degrees. This is a radius. This is the thing that I'm not sure is a tangent yet. And you see that they intersect at 90 degrees at that point of contact. And this is indeed a tangent. And then the other theorem, and this is the one that is mostly used for this type of question, is the tan chord theorem. Again, it's a theorem that relates to tangents. So if you can prove that the angle between this line and a chord is equal to the angle supported by this chord, then it means that this is a tangent. Okay, let's see what we're going to do here. We need to show that EC is a tangent to the circle OEF. So EC, I'll draw this in a different color. So EC is this line over here, and we're trying to prove that it's a tangent to the circle OEF. EF. Let me draw a circle here. Okay, so yeah, clearly here we have to use the tan chord theorem because in this little circle we've drawn, you see that there is no radius. Okay, so if we can show that the tan chord theorem here is true, then this is a tangent. Okay, so this means that we would have to show them that angle E3 is equal to angle O1, and then that would be a tangent. Okay, it's a prove question, so we know that there's something would be required to prove, and now we know that we just have to show them that angle E3 is equal to angle O1, and then this is a tangent. Keep this required to prove in mind. Okay, let's go ahead and look at this. Angle E3 equals angle O1. How can we prove that, given the diagram that we have? You see, you're going to have to think in the direction where you're trying to define both angles. This is one of the easiest ways to get to it if you try to focus on each angle individually. Okay, so sometimes we use I call this the travel method, where we jump from, it's what we did in the previous question. We jumped from this angle to this angle, and then that angle to that angle. It's kind of like traveling through it. But in this case, I'm going to try to define each of it because they're just really in awkward places. This one is at the center, and then this one is here. Okay. Do you see that? Let's try to define angle O1 because this seems like the easier one. It's at the center. The angle at the center is equal to twice the angle at the circumference as long as they're supported by the same chord or arc. So let's say we called angle B2 x, and then of course this would mean that angle B1 is also x. That would make this 2x because it is twice the size of that angle at the circumference B2. Great. Now, if you can show that this would also be 2x, and you don't have to tell them this. You don't have to say, let this be equal to x. It's not necessary. It just helps you on your own to just think it through. So let's see. Let's try to define angle E3. Based on where it is, now look at the diagram as a whole. Based on where it is, angle E3, we have another cyclic chord. And this is on the circle that we have here. This is on these points. So that is the exterior angle of the cyclic chord. Let me highlight that cyclic chord. Okay, that cyclic chord. So do you see that angle E3 is the exterior angle of that cyclic chord? So it's going to be equal to the opposite interior angle, which is x plus x, and that's also 2x. So that's how we would prove that. Now we need to actually just show them how we're doing this. We've figured it out on the diagram, and let's just write it down. So I'm saying that angle O1 is equal to twice the size of angle B2. Okay, so angle O1 equals 2 times angle B2. And this is because of the angle at the center theorem. Angle at the center is twice the angle at the circumference. Okay, so there's our reason. And now that we have that, okay, so that is down. But now let's also just show them that angle O3 is equal to the sum of these two angles because it's the exterior angle of that cyclic chord. Okay, so angle E3 is equal to angle B1 plus angle B2. And we'll tell them the reason, okay, exterior angle of a cyclic chord. And now, remember, we're trying to show that these two are exactly the same. Now, here, we can actually just say, and yeah, this should have been done in this side. Sorry about that. This should have been done here. I should have already thought about this because we already said we're adding these two angles. We can also just tell them, but we already know that angle B1 and angle B2 are equal. This was proven in the previous question. We were able to show them that. Okay, so I'll say that this has been proven. And so this would mean that we can actually rewrite angle O1 as angle O1 is equal to angle B1 plus angle B2. Okay, why can we do that? Because this is 2 angle B2, meaning we're saying that this is angle B2 plus angle B2. So just replace angle B2 with B1 since they are equal. Okay, so that's what we're doing here. And now, because of this, we have shown that angle O1 is equal to B1 plus B2, and angle E3 is also B1 plus B2. So therefore, angle O1 is equal to angle E3. And that's what we were required to prove to ensure that EC is a tangent to the circle OEF. And now we can conclude that. Okay, so conclude and just give the reason. And you see that we used the tan chord theorem. We proved that the tan chord theorem was true, okay, for that circle. Therefore, our reason would be the converse of the tan chord theorem, okay? Okay, because we were not saying that's a tangent. No, we were just proving to them that the angle between the tangent and the chord was equal to the angle supported by that same chord. So therefore, this is indeed a tangent to that circle. And that is our answer. Okay, so that is it for question 9. Question 10, 10.1 says, in the diagram below, triangle ABC is drawn with DE being parallel to BC. And we need to prove the theorem which states that AD over DB is equal to AE over EC. Now, you'll probably notice that this theorem has actually shown up before, and it's specifically in the grade 12 mathematics paper 2 prelim 2022 from the Gauteng province. So I'm actually going to use that explanation because it's in the exact same format to prove this theorem. Okay, and here's the proof. Question 10, 10.1 says, in the diagram below, triangle ABC is drawn. D is a point on AB and E is a point on AC, such that DE is parallel to BC. Use the diagram to prove the theorem which states that AD over DB is equal to AE over EC. Okay, so we're proving the proportionality theorem using this diagram. So to prove the proportionality theorem, we are using the areas of the triangles. And this is because with the areas of the triangles, we will be able to include these sides AD and DB. But we're going to treat AD as the base of this triangle ADE. And so with this base, we're going to find a perpendicular height. That height is going to go from the highest part of the triangle to the base. So if we're treating this as the base, then the height can be drawn from point E all the way to AD, and it needs to be perpendicular to AD. And we can go ahead and call this height H. Now we're going to do the same thing to this side AE. See how we have AE over there? But we're going to look at AE as if that is the base of this triangle again. And to draw a height, we would have to draw this height from this point D all the way to AE, and it is perpendicular to AE. And we can call that height K. Okay, great. Now we have AD and AE that will be included in this calculation. Now, how do we include DB and EC? We can do that by forming triangles that will have these as bases. So for DB to be the base of a triangle, this is how we can do this. DB can be the base of a triangle if we join B and E together. So if this is the triangle and we draw this triangle, you see that this triangle's base BD has been extended. And so the heights would also be drawn as from this highest point E all the way to the extension of that base. Okay, and it is perpendicular to this. So H is also the height of this triangle BDE. And then to include EC in this calculation, we're going to see EC as the base of a triangle, and we're going to draw this triangle by joining D and C together. So now that that has been joined, you see that in this triangle, this is an obtuse triangle, and we have K as the height of this triangle since it has been drawn by extending the base EC. Okay, so all we have to do is write down all the constructions that we have made. Okay, and then once you write your construction, then we can start proving this. Okay, so we're going to use the areas of these triangles because that will help to include these bases, these sides as bases. So here's how we're going to do this. We're going to find the area of this triangle, but looking at AD as the base of the triangle. So the area of triangle ADE But we're going to put this over, and the reason it's going to be over this is because you see we have AD over DB. So we're going to put this over the area of the triangle with the base BD. So over that area. Okay, so that is this triangle BDE. So over the area of triangle BDE. And this is equal to, so the area of a triangle is equal to half multiplied by the base multiplied by the height. So in the triangle ADE, looking at AD as the base, that's the base, and the height is H. Okay, so multiplied by AD multiplied by H. And this goes over the area of this triangle, which is a half, multiplied by its base, and we can see that that base is BD, and then multiplied by the height, which is also H. Okay, they have the same height. Okay, so we also say over H. And then you see with this that these would cancel. We have a half and half cancel, H and H cancels. And so it means that this simplifies to AD over BD. Great. So now we have the AD over BD part. That's done. But now let's get AE over EC. Okay, so we're going to use the areas of those triangles, but using AE as the base and EC as the other base as well. So this is the area, again, of that same triangle, ADE on top, over the area of this triangle with the base as EC, okay? That is this triangle, we can call this CED. And this is equal to a half multiplied by the base of, but this time we're making AE the base of that and then EC the base of this. So it's AE multiplied by the height, and the height of that was K over, and then it's a half multiplied by that base of EC, and the height is also K, as we can see. Okay, so that is the common height in both triangles. And because of this, these also simplify. So a half cancels with a half, K and K cancels, and this is now equal to AE over EC. Great. We also have AE over EC. But we cannot just automatically say they are equal. We're going to have to show them. So with the first one, or with the triangle on top, the area of those triangles, you see how they are the exact same triangle, so we can't tell them that. But we know that the area of triangle ADE is equal to the area of triangle ADE. But now looking at these bottom triangles, because if you can show that these areas are also equal, it will show that their sides, their simplified sides, would also be equal like that, or their simplified proportions. So look at these two triangles that we're looking at on the bottom. So this triangle over here and this triangle over here. Do you see that both triangles lie between the parallel lines DE and BC? So because they lie between parallel lines, it means that their height is exactly the same. If you go from the highest point of the triangle and down, really the heights can be measured like this. You see how the highest points of the triangle are B and C? If you measured it, it's really just from the top there, and if you go perpendicular to DE, that will be the height. So we can see that their heights are exactly the same because they lie between parallel lines. But do you also notice that their bases are the same? If you look at it as if the base is DE, okay? If this is the base and this is the height, the base and height are exactly the same. They're sharing that base of DE. So that's what we're going to say. We're going to tell them that their bases and heights are exactly the same. So we're saying their areas are equal as well. So we'll tell them that we can see that the area of triangle BDE is equal to the area of triangle CED. Okay, and this is because they have the same base, and we can say that that base is DE, and they have the same height because they lie between parallel lines. Okay, and I'll just specify the lines that are parallel, that is DE and BC. So DE is parallel to BC. Okay, and so since their areas are the same, this would conclude that that area of triangle ADE, right, over the area of triangle BDE, that this is equal to the area of triangle ADE over the area of triangle CED. Okay, area of triangle CED. And so what they simplify to would also be equal. So remember how this simplified to AD over BD. So we'll say that AD over BD is therefore equal to, and that's simplified to AE over EC. So AE over EC. And that is how we prove this theorem. Okay, so that is it for this question. Moving on to the next question. Okay, question 10.2 says, in the diagram below, D is the center of a circle. AB and AE are tangents to the circle at B and E respectively. The diameter BG is produced and meets the tangent AE at C, and then we are told that DG is equal to CG. F is a point on AC such that DF is parallel to AB. Okay, so these two lines are parallel. So you can see what they're using there, okay? The proportionality theorem. And 10.2.1 says we need to find with reasons the ratio of AC over FC. Okay, so it's that proportionality theorem because we can see that they are using this triangle with that line drawn parallel to one side of the triangle. Okay, so that means that AC over FC is simply equal to, so it's going to pair with BC over DC. Okay, so BC over DC, we'll just tell them BC over DC. And the reason for this is, of course, because of the proportionality theorem, or you could also say because we have a line drawn parallel to one side of the triangle. Okay, and so the main focus now is just finding out what these ratios would be. Okay, not bad. And the reason why is because, do you see what we have here? We've got DG, right, being equal to CG. So if they're equal, then you can just see them like this. This takes one part, and I'll just call it K. This takes one part. And so whatever this takes, that also takes the exact same thing because they're the same length. But we can also see that this is a circle with a center, and this is a radius, and that's also a radius. The radii are equal, so we know that this is also K. So this ratio would be 2K over a total of 3K, which is just 2 over 3. I just write it in terms of K just so I can keep track of what's going on there. So this will therefore, but before doing that, you actually have to show them that these two are equal. So we'll say BD equals DG. Okay, so BD is equal to, we can just tell them, but we know BD is equal to GD because these are equal radii. And so we already knew that these other two were equal. Okay, so I won't state that. And so that means that AC over FC is equal to, now we can see that BC makes up the entire 3 parts as K plus K plus K. So that's 3K, or say 3 over, and then DC makes up 2 parts. That's K plus K. So that's over 2. If you wrote it as K, the K's would still cancel. So that's why it's fine to write it as this. Okay, so it's 3 over 2, and that is our answer. Moving on to the next question. Question 10.2.2 says we need to prove, given reasons, that triangle ABC is similar to triangle DEC. Okay, let's look at those triangles. So ABC is this triangle. I'll highlight it in red. And DEC, let's highlight that in blue. Okay, so the good thing is they are sharing one angle. Great. So we already have one angle checked in the box. What else do they have that is equal? And we're clearly using their angles here because we don't really have sides. I mean, we have these ratios, but we don't really have any other thing apart from that. So let's see what else we have here. Do you see that this is a radius and this is a tangent? Okay, we were already told that this AE is a tangent. Okay, so the radius and the tangent are perpendicular. Okay, they intersect at 90 degrees. And then this is also a radius and this is also a tangent. That's also 90 degrees. And there we go. We've got 1, okay, 2 angles equal. And then by default, their third angle would be equal. Okay, let's introduce our triangles. So we can go ahead and say in triangle ABC and triangle DEC, that this is what we have. We have that common angle C, so we can just say angle C is equal to angle C, and then we can also see this is 90 degrees here, so angle E1 is equal to 90 degrees because of the tan-co theorem, and so is angle B. So tell them angle E1 is equal to 90 degrees, angle B is also equal to 90 degrees, and then we can just put down the tangent is perpendicular to the radius theorem. Okay, so for this one, we can just say this is a shared angle, and then this is the radius is perpendicular to the tangent at the point of contact, and then the second one gets the same one. And so because of that, in these two triangles, it means that angle E1 is equal to angle B. So these two angles are now equal. So we've got 2 angles equal in each triangle. Then by default, the third angle is equal because the angles must still add up to 180 degrees. So it means that angle A is equal to angle D3. Okay, so we can just conclude that now. Angle A is equal to angle D3, and you can either say third angle in a triangle or say the sum of angles in a triangle. Okay, so those are 3 corresponding equal angles, and so therefore triangle ABC is indeed similar to triangle DEC, and that is because we've got 3 sets of equal angles. So angle, 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 and there we go. So yeah, for this you can just say proven angle. Okay, we're just showing that it's 3 angles that are equal, okay, referring to angles. And that is our answer. Moving on to the next question. Okay, question 10.2.3 says, prove that DE squared is equal to AE multiplied by EC over 3. Okay, let's just pin this to the screen and let's see the lines that they are referring to. Okay, so you see with these questions, if they asked you to prove that 2 triangles were similar in the previous question, and then they present something like this, the first guess should be it has something to do with these 2 triangles being similar. Rather go with that as the first guess before digging into other things, because then it may end up leading you into this whole cycle of trying this and then trying that. So let's go with the most obvious case scenario. Okay, so let's take this because we know that these triangles are similar, and we're going to pick out the sides that we see here. So I see DE squared, yeah, but DE is there. And DE is in this triangle, okay, DE. So it means that when we take them, okay, as ratios, we're going to have to take it as AB over DE. So this is AB over DE is equal to, and then looking at this here, because we already have DE, now what else do they have here? They have EC. They don't have AE, but they have EC. So we can take EC, and then we're going to pair that with BC. So it goes with the second and third, so that's the second and third as well. So that is BC over EC. And this is because we have similar triangles. Okay, let's see how we can form this. So they clearly cross-multiplied, and they got DE squared at some point. And of course, there's also that 3. That 3 is, yeah, we know something about 3 from the way this diagram looks, okay? This is K, and this is K, and this is K, and this is BC. That's also what we have, BC. Okay, so that's clearly where they got that from. So let's actually look at this entire thing and look at our diagram now and see how this relates with it, if we can actually get to this. Okay, so this is our diagram, and I've just pinned this. So looking at this, AB, okay, we've got AB, and we know that somehow, okay, it multiplies across like this, but then it will end up being DE squared, okay, because we have DE here, so clearly it must have multiplied to BC. Okay, so it's DE and BC. Let's look at BC. What is BC? Okay, BC is this entire length, right? Which I've just called each of them K, just so that I know that they take 1 part each, and then altogether they make up 3 parts of the exact same length. So how does that relate to DE? Because clearly it must have become a DE. How does this relate to DE? DE is over here, okay? And DE is a radius. That is good. Okay, so here it is. DE is a radius from the center to the circumference. DG is also a radius from the center to the circumference. And you see that DG, right, is equal to GC. So it's kind of like if this takes K parts and that takes K parts, and this is the exact same length, then it means that BC is made up of 3 times DE. Okay, but we're going to have to state that down properly. So we can start by saying it was given that DG was equal to GC, right? We can tell them we knew that DG was equal to GC, and this was already given. But now from the diagram, we can also see that DG is equal to DE and BD. That's also a radius, okay? And because they are all radii, so we'll say that DG equals DE and BD. I'll start with DE. Say DE equals DG and BD, okay? And this is because all 3 are radiuses that we have, so equal radii. And now because of that, we can actually write BC in terms of DE. Okay, so since they're all equal, it means that the entire length of BC is 3 sets of DE. So that's DE plus DE plus DE, and that's 3DE. Okay, so that means that BC is actually equal to 3DE. Great. Okay, let's fill that in our diagram and just see how we can still get to that. So therefore, this means that AB, I have no idea what AB is, we'll see, over DE is equal to BC, which is 3DE over EC. And we can look at that and see how we can get to this that we have to prove. So you see now that if you cross multiply, you're going to get that 3DE squared. And the 3 is not a problem because you can still divide by 3 to get it back on that denominator. Okay, let's just cross multiply so long so we can just see what we need to find. So this is now DE squared, 3DE squared specifically, is equal to, and then AB times EC. So that's AB times EC. Okay, so from this, we can actually see that the only thing that we need to find is AB. This is actually working out perfectly well. And we just have to find out exactly what AB is. So at this point, yes, you can just divide both hand sides by 3. So that so long we have DE squared is equal to, let me just move this, we have AB multiplied by EC over 3. Okay, now you see how they look identical. The only difference is here you have AE and here you have AB. So let's find out what AE is. And how is it equal to AB? Let's look at AB and AE, those lines. Okay, so with AB and AE, this is AB, this is AE. Why and how are these lines equal? Okay, so remember how they said these are tangents. If you get lost with these things, so you just lose track of what was going on, you can go back to the information and read just to see anything you may have missed. AB and AE are tangents. So they are tangents drawn from the same point, A, to this circle. So they will be equal. So from A to E, that is equal to A to B. And now we can actually just state that. So we can tell them that AB is equal to AE because these are tangents from the same point. And now we can just replace AE with AB. So therefore, DE squared is indeed equal to AE multiplied by EC over 3. And that is our answer. Moving on to the next question. Question 10.2.4 says we need to find the ratio of the area of triangle FDC over the area of triangle ABC. So FDC over ABC. Okay, so you see ABC is already highlighted. I'm just getting rid of these. And FDC is just this one here. Okay. That's good because this is that triangle that is similar to it. We don't really have to prove any similarity. It's not necessary. We have enough to prove this. So do you see that with these triangles, they are sharing an angle, okay, angle C. So the best way to prove this using their areas would be to use the area rule, not a half times the base times the height, because now we would have to find a logical height that we could use there. And that can be stressful in this situation. Just go for this one because we have a common or shared angle. Okay, so we're going to use the area rule here. And so to use the area rule here, you see in the red triangle, we would need the sides next to this common angle. So we're using this angle and we would need AC, at least a ratio for AC, and BC, okay? And then we would need a ratio for FC and DC. But we already found these, okay? Because I remember I wrote K here, meaning we already found a ratio for them. So, and that was actually in the beginning. So initially, do you see that we found that AC over FC is equal to 3 over 2? So I also just named them in terms of letters. So FC takes a ratio of 2, and then AC takes a ratio of 3. Okay, that's where we got that 3 over 2, AC over FC. Now, I would usually in the diagram, but it's the last question, that's why I'm not really bothering too much about that. I usually call it like 3A and 2A just to show that this is the ratio it gets depending on the line it is on. But again, it's not that necessary because this is the last question. So we just know that we're using these sides. Okay, I'm going to screenshot this and then pin it there so that we can just work on it in that question. Okay, so we are taking the area of triangle FDC over the area of triangle ABC, and it's equal to, so area of triangle FDC, we'll say a half, multiplied by, so using the area rule, so this blue triangle, we would say multiply by the side next to that angle that we have, okay, so that is FC, multiplied by the other side, which is DC, and then we'll say sine of that common angle, that center angle, which is angle C. And this goes over a half multiplied by, in the red triangle, we're taking AC, so AC multiplied by BC, and then sine of angle C. Now, because of this, you see how sine of angle C and a half cancel. Those are gone. So all we have to find are ratios for these sides. So FC, if you like, you can call it 2A, you can call it 2, it's still fine because look at what happens. If we say FC was 2A, right, and then multiply by DC, DC was, as you can see, that's going to be 2K, okay, DC. So that's 2K over, and if we say AC, which is 3A, multiplied by BC, which is 3K, then you see that the A and the K's would just cancel because regardless of what they were, their ratios will still simplify like that to 2 over 3 and 2 over 3. So those cancel and you have 4 over 9. And that is our answer. Okay, that's what that simplifies to. And that is it for question 10. Okay, so that is it for this paper. And I hope you guys enjoyed it. And I will see you guys in the future videos.